Even though the universe is already unbelievably huge, scientists keep saying it's still expanding. But what does that really mean? When we hear expansion, we usually imagine things moving apart through space. That's not exactly what's happening here. Instead, it's space itself that's stretching. Galaxies aren't moving through space to get farther apart. They're being carried away as the space between them grows. So, if nothing exists beyond it, then what is it actually expanding into? Is there something beyond it, or is space itself infinite? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there now. Now, settle in for a journey to uncover what the universe is truly expanding into. For a very long time, both scientists and philosophers have had to deal with one of the most confusing and puzzling questions. What does it mean for there to be nothing? At first look, the answer might seem simple. Nothing seems like an empty box, a dark space, or a place where no objects, no air, and no light exist. But when the question is looked at more carefully, the idea of nothing quickly becomes one of the most mysterious and hard concepts in human thought. Different areas of study, philosophy, physics, and cosmology, give very different answers. For philosophers, absolute nothingness means the complete absence of everything, a state where there is no matter, no space, no time, no energy, and no rules. For modern science, especially in quantum physics, the word nothing often points toward what is called the quantum vacuum, which is not truly empty, but is instead full of restless activity. To understand the difference between absolute nothingness and the quantum vacuum is to enter a world where our language struggles to describe ideas too strange for daily life, but too important to ignore when asking how the universe itself began. When most people hear the word nothing, they usually think of blankness or emptiness. If one were to close one's eyes in a pitch-dark room, one might believe that one is looking at nothing. Yet, even in the darkest room, there is still air. There is still one's body, there is still time passing, and there are still atoms moving around. So what most of us call nothing in everyday speech is not real nothingness at all. It is simply a space that lacks the objects we usually expect. Philosophers thousands of years ago already noticed this. Ancient Greek thinkers like Parmenides argued that nothing could not exist because the very act of speaking about it already gives it a kind of existence. On the other hand, thinkers like Democritus and later Epicurus spoke of the void, which they believed was a necessary background against which atoms, the building blocks of matter, could move. Even at the very birth of philosophy, nothingness was more than just an absence. It was a puzzle. As human thought developed, the idea of nothingness became tied to questions about creation. Religious traditions often begin with a story of creation out of nothing. The Latin phrase creatio ex nihilo means creation out of nothing, and it became central to the teachings of Christianity, Judaism, and Islam. In these traditions, God does not shape the world from pre-existing stuff, but instead brings the universe into being out of absolute nothingness. This raises the question, what exactly is this nothing that comes before creation? If it truly has no qualities, no rules, and no potential, how could anything ever come from it? And yet, if it has some kind of hidden potential, is it still nothing? The paradox of nothing becomes sharper here because one cannot even point to it without giving it some kind of presence. Philosophy continued to wrestle with this puzzle for centuries. In the 17th century, René Descartes spoke of nothingness in connection with God's infinite power. In the 18th century, Immanuel Kant argued that the human mind could not truly picture nothingness because our thoughts are always shaped by space and time, and absolute nothingness lies beyond both. Later, in the 20th century, existentialist thinkers like Jean-Paul Sartre explored nothingness not as a physical idea, but as an emotional and mental reality, something tied to human freedom, anxiety, and the feeling of absence in life. For philosophers, then, nothingness often remains a deep and absolute idea. It is the absence of being itself, a void so deep that it cannot even be measured. Science, however, takes a different approach. In physics, the word nothing has never meant the same thing as it does in philosophy. For most of history, scientists thought of empty space as a true void, a stage with no actors. but discoveries in the 19th and 20th centuries broke that view. When Albert Einstein introduced his theory of relativity in the year 1905 and later in 1915, space and time were no longer seen as an empty container. Instead, they became a flexible fabric that could stretch, bend, and ripple under the influence of mass and energy. What people once called empty space now seemed to have structure and properties of its own. Still, relativity did not yet show just how busy this emptiness really was. The real change came with the birth of quantum mechanics in the early 20th century. Quantum theory showed that the smallest building blocks of nature do not behave like solid billiard balls, but instead like waves of possibility. They flicker in and out of being, appearing here and there, guided not by certainty but by chance. Out of this strange world came the realization that even when all matter and radiation are removed from a region of space, there is still something there, the quantum vacuum. This vacuum is not a calm nothingness, but a restless sea of invisible changes. Tiny particle-antiparticle pairs constantly pop into existence and then vanish almost instantly. These virtual particles, as physicists call them, cannot be directly seen, but their effects can be measured. For example, the Casimir effect, first predicted in 1948 by the Dutch physicist Hendrik Casimir, shows that two uncharged metal plates placed very close together in a vacuum will attract each other because of these quantum changes. In other words, the vacuum is not empty at all. It hums with energy. The difference between absolute nothingness and the quantum vacuum now becomes clear. Absolute nothingness, as imagined in philosophy and theology, would be the total absence of anything at all. No particles, no forces, no space, no time, and no laws of physics. It would be a state of pure absence, a reality that cannot even be described because description already assumes something exists. The quantum vacuum, by contrast, is not truly nothing. It is a low-energy state of a physical system, but it still contains space, time, quantum fields, and restless activity. If one clears out a box of all matter, light, and heat, quantum mechanics says that one is still left with vibrating fields and occasional flickers of particle activity. This vacuum is as close to nothing as science can get, but it is not the same as the absolute void of philosophy. This difference has huge effects on our understanding of the universe. If philosophers are right that absolute nothingness is beyond existence, then the question of how something comes from nothing might be impossible to answer. But if the scientific picture is correct, and the vacuum is never truly empty, then the universe may not have started from absolute nothingness at all. Instead, it could have arisen from the quantum vacuum, where changes can give birth to particles, energy, and perhaps even entire universes. Some physicists, like Lawrence Krauss, have argued that modern cosmology shows how a universe can arise from nothing, but what they really mean is from the quantum vacuum, not from the pure, absolute nothingness that philosophers describe. This has led to heated debates because critics point out that if one begins with space, time, and quantum laws, then one does not truly begin with nothing. The question then deepens. Is the quantum vacuum itself something that needs an explanation? Why is there a vacuum at all, with rules and fields that allow changes? Why is there not instead absolute nothingness? This question pushes the limits of both science and philosophy, and it may never be fully answered. Still, exploring the quantum vacuum has revealed wonders that change how we think about emptiness. For instance, quantum field theory predicts that the energy of the vacuum is not zero, but instead has a certain vacuum energy. When Albert Einstein first introduced the cosmological constant in 1917, he thought of it as a math trick to keep the universe from collapsing. But in modern cosmology, the cosmological constant is often linked to vacuum energy, and it may explain the mysterious dark energy that is causing the universe to expand faster and faster. Thus, what we call empty space is actually one of the most powerful forces shaping the cosmos. To understand just how strange the quantum vacuum really is, let's return to those tiny fleeting particles that seem to appear out of nowhere. These are called virtual particles, and they are very different from the particles we usually think of, like electrons or protons, which can be weighed and directly observed. Virtual particles are more like a hidden presence. They exist only in the equations of quantum physics, yet their effects are real and measurable in experiments. They influence how forces behave, they slightly shift the paths of electrons, and they even contribute to the mass of the proton itself. Without these tiny fluctuations, the chemical reactions that shape the universe might work completely differently, and life as we know it might not exist. In this sense, the nothing of physics is far from empty. It is a secret, active stage where the entire drama of matter and energy takes place. Even with all this scientific knowledge, the deeper philosophical puzzle remains. If the vacuum is something, then we still have not answered the oldest question. Why is there something rather than nothing? If the rules of quantum physics allow these fluctuations, why do those rules exist at all? Could there have been a reality with no rules, no fields, no vacuum, literally nothing at all? Some philosophers argue that the idea of absolute nothingness is impossible to make sense of. It cannot even be imagined or described without contradiction. Others think it could be a real possibility, a quiet mystery behind everything we see. Either way, comparing absolute nothingness to the quantum vacuum shows just how limited human understanding is. To make this even clearer, imagine if it were possible to step inside these two types of nothingness. Absolute nothingness cannot be pictured at all, because even imagining entering it assumes there is a space and a time to do so. If you try to picture it, you might think of a blank black void, but even that is already something. Black is a colour, a void is a space, and to see it is to exist inside it. Absolute nothingness has no colour, no space, no seeing, no thing at all. It is beyond imagination. The quantum vacuum, by contrast, can at least be described. At first glance, it seems empty, a silent dark space with no matter, no light, no heat. Yet underneath that apparent emptiness, invisible storms are constantly occurring. Particles flicker into existence and vanish again, energies shimmer and fade, and fields tremble with unseen motion. The quantum vacuum is not truly empty. It is a restless void, full of potential, ready to give birth to new realities. This distinction changes the story we tell about the origin of the universe. In traditional philosophy or theology, the universe might have come from absolute nothingness, through a divine act or a mysterious metaphysical leap. In modern physics, the universe could instead emerge from the fluctuations of the quantum vacuum, without needing anything outside itself to start the process. The Big Bang, which happened around 13,800,000,000 years ago, may have been the moment when such a fluctuation exploded into the expanding universe we see today. But whether this counts as the universe coming from nothing depends on how you define nothing. For philosophers, it is not truly nothing. It is something very strange and mysterious. For scientists, it is close enough to nothing to serve as a real explanation. The concept of an expanding universe is more than just the idea that galaxies are drifting away from each other through space. It is not that stars and galaxies are racing across an empty void, moving from one place to another. Instead, it is the very fabric of space between them that is stretching. This distinction is extremely important because it changes the way we understand the universe and its structure. When scientists talk about the expanding universe, they mean that space itself is gradually getting larger over time. A useful way to picture this is to imagine the universe as a balloon. Galaxies are like tiny dots drawn on the balloon's surface. As the balloon slowly inflates, the surface stretches and the dots move farther apart. But the dots are not moving on the surface. The surface itself is growing, and it is this stretching that separates the dots. In a similar way, galaxies move apart in the universe not because they are travelling through space, but because space itself is expanding. This idea changes how we normally think about space. Usually we imagine space as a fixed stage where planets, stars and galaxies simply exist and move. But in an expanding universe, space is not fixed. It is dynamic, constantly stretching and reshaping itself. As a result, the farther away a galaxy is, the faster it appears to recede from us. This happens because more space is expanding between us and that distant galaxy. This is why galaxies that are billions of light years away seem to be moving away at astonishing speeds. One of the most surprising consequences of this expansion is that there are galaxies so distant that we will never be able to see them. The space between us and these galaxies is growing so rapidly that the light they emit can never reach Earth. It is as if the expansion of space itself carries them beyond our vision. This means that even though the universe contains an immense number of galaxies, there are regions of it that will always remain beyond our reach. These areas are part of what scientists call the observable universe, the portion of the universe from which light has had enough time to reach us since the universe began, approximately 13,800,000,000 years ago. Another important point is that the expansion of the universe does not pull apart galaxies, stars, or planets that are close together. For instance, the Earth and the Sun are not being separated by the expanding space between them. This is because the expansion only becomes noticeable over vast distances. Gravity holds solar systems, stars, and galaxies together, so the stretching of space is only significant when we look at distances between far apart galaxies, not within them. Finally, the fact that space itself is expanding means there is no central point from which the universe is growing. There is no center of the universe. Every point in space stretches outward, and from the perspective of any single galaxy, all other galaxies appear to be moving away. This was an extremely challenging idea for scientists to accept at first because it conflicts with our everyday experiences. Normally, we think of objects moving relative to a fixed background, but in the universe, the background itself is changing. The story of the universe's expansion does not start with a gentle stretching of space. In fact, right after the Big Bang, the universe went through an astonishingly brief but unbelievably intense phase called inflation. This inflationary period lasted only a tiny fraction of a second, yet it shaped the universe in ways that still affect everything we see today. In the moments immediately after the Big Bang, the universe was an incredibly hot, dense soup of particles and energy. Almost instantly, however, space itself began to grow at a mind-boggling speed, far faster than the universe expands now. During this inflationary burst, the universe expanded from a size smaller than an atom to a scale spanning light years, all in less than a single second. This extraordinary growth smoothed out any extreme irregularities, making the universe remarkably uniform, while also creating tiny variations in density. These small fluctuations would eventually become the seeds of galaxies, stars, and planets. Without this period of inflation, the universe as we know it might never have formed in a way that could support life. Inflation spread everything out, creating a vast and mostly even universe, but with slight differences that allowed structures like galaxies and clusters of galaxies to form later. After inflation ended, the universe continued to expand, but at a much slower pace, gradually shaping the size and structure we observe today. For a long time, scientists assumed that this slower expansion would continue to decelerate because the gravitational pull of galaxies, stars, and other matter should be slowing everything down. However, in the late 1990s, astronomers made a shocking discovery. The universe's expansion is not slowing, it is speeding up. This discovery came from studying distant supernovae, which are enormous explosions that occur when certain stars reach the end of their lives. Two separate teams of astronomers carefully measured how fast the universe was expanding in the past compared to now. To their surprise, they found that these faraway supernovae appeared dimmer than expected. This meant that the galaxies hosting them were farther away than they should have been if expansion was slowing down. Something, they realized, was pushing the universe to expand faster, not slower. This mysterious force was given the name dark energy, and it remains one of the greatest mysteries in modern science. Dark energy makes up roughly 70% of the total energy of the universe, yet its exact nature is still unknown. Scientists only know that it behaves like an invisible force that counteracts gravity, pushing galaxies apart at an ever-increasing rate. Unlike ordinary matter or even dark matter, dark energy does not clump together. Instead, it appears to be evenly spread throughout space, influencing the universe on the larger scales. Understanding dark energy is one of the biggest challenges in cosmology today. It plays a crucial role in shaping the future of the universe, but its nature remains elusive. One possibility is that dark energy is a property of space itself. According to this idea, as space expands, more space is created, and with it, more dark energy. This would mean that the expansion of the universe actually fuels itself, with dark energy becoming stronger as the universe grows larger. Another idea links dark energy to the cosmological constant, a concept first introduced by Albert Einstein in his equations of general relativity. Einstein originally included the cosmological constant to keep the universe static because at that time, scientists had not yet realized that the universe was expanding. After Edwin Hubble's observations in the 1920s revealed that galaxies were moving apart, Einstein removed the constant, calling it his biggest blunder. But the discovery of dark energy has revived interest in this concept. Some scientists now think that the cosmological constant could represent a built-in form of dark energy, woven into the very fabric of space. The presence of dark energy raises profound questions about the ultimate fate of the universe. If the expansion continues to accelerate, what could happen in the distant future? One possibility is a big freeze, where galaxies drift so far apart that stars eventually burn out, leaving a cold, dark, and empty universe. Another scenario is a big rip, where expansion accelerates so drastically that even galaxies, stars, and eventually atoms themselves are torn apart. Although these outcomes remain speculative, they show just how important dark energy is in shaping the long-term destiny of everything in the cosmos. The story of cosmic expansion is far from finished, and the universe still holds secrets that may challenge our understanding of reality itself. The universe has not been expanding at a steady, unchanging pace over billions of years. The speed at which space stretches has varied throughout its history. Right after the Big Bang, during a brief but extremely rapid phase called the inflationary period, the universe expanded at an almost unimaginable rate. Once this inflation ended, the universe continued to grow, but much more slowly. Gravity, the force that pulls matter together, worked against this expansion, trying to slow it down. For a long time, the expansion of the universe was a careful balance between the outward push from the Big Bang and the inward pull of gravity. This tug-of-war shaped the way the universe developed. To understand how fast the universe is expanding, astronomers use a number called the Hubble constant. The Hubble constant tells us how quickly galaxies are moving away from one another based on how far apart they are. It is a key number in cosmology because it helps scientists figure out the age, size, and possible future of the universe. The Hubble constant is usually expressed in kilometers per second per megaparsec. A megaparsec is a unit of distance used in astronomy, equal to about 3,260,000 light-years. So, if a galaxy is 1 megaparsec away, the Hubble constant tells us how fast it is moving away from us in kilometers per second. The farther a galaxy is, the faster it appears to be moving away, and the Hubble constant helps quantify this relationship. Measuring the Hubble constant requires extremely precise measurements of both the distances to galaxies and how fast they are moving away. One of the main ways astronomers measure distances to faraway galaxies is by using a type of star called a Cepheid variable. Cepheid variables are stars that regularly pulsate, getting brighter and dimmer over time. The important feature of these stars is that the period of their pulsation is directly connected to their true brightness. By comparing how bright a Cepheid actually is with how bright it appears from Earth, astronomers can calculate how far away it is. Once they know the distance to a galaxy, they can measure how fast it is moving away by looking at the redshift of its light. As galaxies move away, their light stretches into longer, redder wavelengths. The amount of redshift gives a clue to the galaxy's speed. With both the distance and speed of a galaxy, astronomers can calculate the Hubble constant. Although the concept of measuring the Hubble constant is straightforward, finding its exact value has proven to be tricky. Different teams of astronomers have arrived at slightly different measurements, leading to a situation known as the Hubble tension, a scientific debate about the precise value of the Hubble constant. There are two main methods used to calculate the Hubble constant, and they do not perfectly agree. The first method is more direct. It measures the distances to galaxies and their redshifts using objects like Cepheid variables and supernovae as distance markers. This approach focuses on galaxies relatively close to us and gives a Hubble constant of about 73 kilometers per second per megaparsec. The second method relies on studying the early universe, particularly the cosmic microwave background, or CMB. The CMB is the faint afterglow of the Big Bang, a kind of snapshot of the universe when it was only 380,000 years old. By analysing patterns in the CMB, scientists can calculate how fast the universe was expanding shortly after the Big Bang, and then use models of cosmic evolution to estimate the Hubble constant today. Measurements from this method suggest a slightly lower value, around 67 kilometers per second per megaparsec. Although the difference between 73 and 67 might seem small, it is significant enough to raise questions. If our understanding of the universe's expansion were complete, both methods should give the same result. The fact that they do not suggest that something could be missing from our current models of the universe. One possibility is that there is some unknown aspect of physics we have not yet discovered. Our models rely on certain assumptions about dark energy, dark matter, and the behavior of gravity. If any of these assumptions are slightly off, it could explain the differences in measurements. For example, if dark energy does not behave exactly as we think, it could affect the expansion rate in ways we have not accounted for. It is also possible that the universe contains some form of exotic matter, or energy, that has not been detected yet. This mysterious substance might have influenced the early universe differently than it does today, leading to discrepancies between measurements from the early and present-day universe. Another idea is that gravity might work differently over enormous cosmic distances. Einstein's theory of general relativity has been extremely successful at describing gravity on smaller scales, such as within our solar system or even within individual galaxies. But we have never directly tested how gravity behaves across the larger scales of the universe. If gravity behaves even slightly differently across these vast distances, it could affect the rate of expansion in ways we do not fully understand yet. Some scientists have suggested modifications to general relativity to account for this possibility. To make the picture even more complicated, some researchers wonder whether the Hubble tension is a real problem or simply an issue with our measurements. Measuring distances in space is extremely difficult, and even small errors can affect the calculations. For instance, uncertainties in understanding the properties of Cepheid variables or supernovae could slightly skew distance measurements, and therefore the estimated Hubble constant. Similarly, analysing the CMB relies on complex models of how the universe evolved in its earliest moments. If there are errors in these models, they could also impact the predicted value of the Hubble constant. Scientists are revisiting these models to ensure nothing was missed or misinterpreted. Over time, the rate of the universe's expansion has changed. In the early universe, gravity played a major role in slowing down the expansion. Galaxies were closer together, and their gravitational pull on each other was stronger. As the universe grew, galaxies moved farther apart and the force of gravity weakened. When the universe was about 9,800,000,000 years old, around 4 billion years ago, the expansion rate began to speed up again, driven by dark energy. With new technologies, astronomers hope to get closer to the true value of the Hubble constant. Advanced telescopes and observatories, such as the James Webb Space Telescope, are helping scientists refine their measurements and move toward a more accurate understanding of how fast the universe is expanding. The quest continues, as each new observation brings us a little closer to answering one of the most fundamental questions about our cosmos. The expansion of the universe raises fascinating questions about how gravity, one of the fundamental forces of nature, interacts with the stretching of space on the grandest scales. Observations show that the universe is expanding, and as a result, galaxies are gradually moving away from each other as space itself stretches. But on smaller scales, like inside individual galaxies or clusters of galaxies, gravity seems to hold everything tightly together. These two forces, cosmic expansion and gravity, are constantly interacting, shaping the structure of the universe in ways that sometimes seem contradictory. Gravity, as described by Albert Einstein's theory of general relativity, is the invisible force that pulls matter together. It is responsible for the orbits of planets around stars, the formation of galaxies, and the grouping of galaxies into clusters and superclusters. Without gravity, matter would be scattered randomly across space, rather than forming the beautiful structures we see today. Gravity works because mass bends the fabric of space and time, drawing objects toward each other. The larger the mass of an object, the stronger its gravitational pull. At the same time, the universe is expanding, driven by the stretching of space itself. Galaxies are not moving through space like cars on a road. Instead, it is the space between them that is growing, slowly carrying them farther apart. This expansion is most noticeable on the larger scales, affecting galaxies and clusters that are millions or even billions of light-years apart. Within smaller systems that are bound together by gravity, such as individual galaxies, this cosmic expansion has very little effect. For example, in a single galaxy, the combined mass of stars, planets, and dark matter creates a strong gravitational field that keeps everything tightly bound. On these scales, the expansion of space is so weak that it is essentially cancelled out by gravity. On these scales, the expansion of space is so weak that it is essentially cancelled out by gravity. This is why we do not see galaxies themselves stretching, or stars drifting away from one another. Gravity keeps them firmly in place. The expansion of the universe only becomes obvious when we look at objects separated by vast cosmic distances. Even galaxies that seem relatively close, like our Milky Way and its neighbouring galaxy Andromeda, are not moving apart because of cosmic expansion. In fact, they are actually heading toward each other, drawn together by their mutual gravitational pull. The gravity between them is strong enough to overcome the stretching of space in their local region. Even within clusters of galaxies where hundreds or thousands of galaxies are bound together, gravity dominates. These clusters are some of the largest structures in the universe held together by gravity, while the space between clusters continues to expand. The galaxies within a cluster orbit around a shared centre of mass, and gravity keeps them bound despite the overall cosmic expansion. Over very long timescales, the expansion will gradually push clusters farther apart, but within each cluster, gravity still holds sway. Scientists are still exploring what might happen if the universe continues to expand at an accelerating pace, driven by a mysterious force called dark energy. Some predictions suggest that if dark energy becomes strong enough, it could eventually overpower gravity, tearing galaxies, stars, and even atoms apart in a scenario called the Big Rip. In this hypothetical future, space itself would expand so violently that nothing could remain bound together, and the universe would end in complete emptiness and isolation. But for now, gravity continues to hold its ground. There is another critical aspect of this balance between gravity and cosmic expansion: dark matter. Dark matter is an invisible form of matter that does not interact with light, yet it makes up the majority of mass in galaxies and clusters. It is the gravitational pull of dark matter that keeps galaxies from flying apart, even when the visible matter, like stars and gas, is not sufficient on its own. Without dark matter, galaxies would lack the mass needed to generate strong gravitational fields, and would be more affected by cosmic expansion. By adding hidden mass, dark matter allows gravity to overpower the weak pull of expansion within galaxies, making it a crucial piece of the puzzle in understanding how the universe stays structured while it grows ever larger. As the universe continues to expand, the galaxies far away from us are moving away at a speed that keeps increasing. This is not just ordinary movement through space, but rather a result of space itself stretching, carrying entire galaxies along with it. The further away a galaxy is, the faster it seems to recede, and eventually, the speed at which it moves away can surpass the speed of light. This might seem impossible at first because we are often told that nothing can travel faster than light. However, this rule applies to objects moving through space, not to space itself. Space can stretch without limit, and as it does, it can carry galaxies with it faster than light ever could on its own. This is a key idea to grasp when thinking about the long-term fate of distant galaxies and the universe as a whole. As space expands, the distance between us and faraway galaxies grows larger and larger. At some point, these galaxies will move away so rapidly that the light they emit will never reach us. They will not disappear in the sense of vanishing completely. They will continue to exist, but from our vantage point they will effectively vanish beyond our ability to see them. Over immense spans of time, the observable universe, the portion we can detect with our telescopes, will shrink, leaving us surrounded by emptiness. Even now, there are galaxies so distant that their light has only just arrived, travelling across billions of light years. In the future, as these galaxies drift farther apart, the light they emit will be stretched to longer wavelengths, becoming harder and harder to detect. This stretching of light is known as redshift. As a galaxy moves away, the waves of light it emits are stretched, shifting toward the red end of the spectrum. The faster a galaxy recedes, the more its light is redshifted, and eventually it moves beyond the range of visibility. Even our most sensitive telescopes will no longer detect it. Billions of years from now, most galaxies will have moved beyond what is called the cosmic horizon, the limit of what we can observe. Only galaxies that are gravitationally bound to our own, like the Andromeda Galaxy, the Milky Way, and a few smaller nearby galaxies, will remain visible. These galaxies, pulled together by gravity, will not drift away in the same way. Instead, they will remain relatively close and may eventually merge into a single massive galaxy. Beyond this small local group, all other galaxies will fade into the darkness, leaving our universe, from our perspective, increasingly empty. This vision of the future shows a universe growing lonelier over time. As each galaxy slips beyond the cosmic horizon, the light carrying information about its past is lost to us. Future observers, looking out from our galaxy or from the massive galaxy that results from mergers, might have no idea that an enormous universe full of countless galaxies ever existed. Once distant galaxies vanish, interactions between galaxies will become rare. In the early universe, galaxies often collided and merged, forming larger structures and sparking waves of star formation. But as the universe stretches and distances grow, these cosmic dances will become increasingly uncommon. The universe will become quieter, emptier, and more isolated. Long after distant galaxies have disappeared beyond the cosmic horizon, the stars within our galaxy will continue to burn for billions of years, but eventually even they will exhaust their fuel and fade. The universe will grow colder and darker as new stars are no longer born and old stars die. This era, sometimes called the heat death of the universe, marks a state where the universe has expanded so much that the dynamic processes that shaped its early evolution can no longer take place. The accelerating expansion of the universe also raises deeper questions. Could this stretching of space somehow influence the laws of physics themselves? The constants of nature, the speed of light, the strength of gravity, the fine structure constant that governs how light interacts with charged particles, are thought to remain fixed, providing a stable framework for how matter and energy behave. But some theorists wonder whether the ongoing expansion might subtly affect these constants. Even slight changes could produce a universe very different from our own. For example, the speed of light sets the ultimate pace for how information travels through space. Gravity determines how strongly objects attract each other, and the fine structure constant controls how atoms form and how light interacts with matter. If any of these were even slightly different billions of years ago, the universe might have formed in ways we cannot yet fully imagine. Some studies hint that the fine structure constant may have been slightly different in the ancient universe, though this is still debated. If true, it could mean that cosmic expansion or other cosmic processes subtly shape the laws of physics over time. The stretching of space also affects how we perceive time. As distances grow and light is redshifted, it is natural to wonder whether the flow of time itself could be influenced by the expansion of the cosmos. Some speculative theories propose that as the universe expands and cools, entirely new forms of physics might emerge. The laws that govern high-energy processes could shift, fundamental forces might change, and the universe could undergo phase transitions. Transformations similar to how water freezes into ice under certain conditions. In this scenario, billions or even trillions of years from now, the universe might follow rules very different from the ones we know today, giving rise to a reality almost unimaginable from our present perspective. The light from distant galaxies can take millions, or even billions of years to finally reach our eyes here on Earth. Because the universe is constantly stretching and growing, the farther away a galaxy is, the older the light we see from it becomes. It is as though we are looking at snapshots of the past captured long before our planet even existed. However, there is a boundary to how far we can see, a limit known as the cosmological horizon. This horizon marks the edge of the universe that is observable to us, defining the furthest distance from which light has had time to reach Earth. Beyond this invisible boundary lies a vast expanse we cannot observe. This does not mean the universe stops there, far from it. Beyond the horizon, there may be countless galaxies, stars, and cosmic structures, but their light has not yet had enough time to travel the enormous distances to us, and so they remain hidden from our view. Interestingly, nothing can travel faster than light through space, but space itself is not limited in the same way. Space can expand at any speed, carrying galaxies along with it. This means that the light from galaxies beyond a certain distance is stretched and redshifted so much that it effectively disappears from our view. In other words, even though these galaxies exist, we cannot see them because their light cannot catch up to the expanding universe. The observable universe is just the portion of the cosmos that is within this horizon. It is constantly changing. As time moves forward, light from more distant regions gradually reaches us, slowly increasing the size of the observable universe. But because the expansion of the universe is accelerating, some galaxies that are visible today may eventually drift beyond the cosmological horizon. Their light will stretch even further, shifting toward longer wavelengths until they vanish from detection altogether. So, while the observable universe grows, the number of galaxies we can see might actually decrease over time as space expands faster and faster. Everything we know about the universe comes from the light that has reached us, and this light carries the story of cosmic history across billions of years. But beyond our horizon lies an enormous, inaccessible expanse. There could be galaxies, massive structures, and perhaps entirely different regions of the universe that we may never be able to see or study. One of the key factors defining the cosmological horizon is the age of the universe. Our universe is around 13,800,000,000 years old, and since light travels at a finite speed, we can only see objects whose light has had enough time to arrive here. This means the most distant objects we can observe appear as they were about 13,800,000,000 years ago. Yet because the universe has been expanding during this entire period, the actual distance to these faraway objects is far greater than 13,800,000,000 light-years. In fact, today, the edge of the observable universe is estimated to be about 46 billion light-years away. This may seem puzzling at first, but it makes sense when we consider that space itself stretches. As light travels toward us from distant galaxies, the space between grows, pushing them farther away. So, although the light we see has travelled for 13,800,000,000 years, the galaxies themselves are much farther from us today because of the continuous expansion of the universe. The cosmos is vast, ever-changing, and full of mysteries just beyond the reach of our sight. The cosmological horizon marks the farthest boundary of what we can observe in the universe, but it is not the edge of the universe itself. Beyond this horizon, the universe almost certainly continues, stretching into regions we can never directly see or reach. For decades, scientists have been captivated by the mystery of what might exist beyond this invisible boundary, leading to many theories, ideas, and even wild speculations about the nature of those distant, unreachable parts of space. One of the simplest ideas is that the universe beyond the horizon is much like the part we can see. This idea comes from the principle of cosmological homogeneity, the assumption that, on a large scale, the universe is uniform and looks the same in every direction. According to this idea, if we could somehow peek beyond the observable universe, we would likely find more galaxies, stars, and cosmic structures similar to those we know, suggesting that our observable universe is just a tiny portion of a much larger, possibly infinite cosmos. However, some scientists believe that the universe might not be uniform beyond what we can see. While the observable universe seems smooth and evenly spread out, there could be regions beyond our horizon where matter and energy are distributed very differently. Some areas might be packed with galaxies, stars, and gas, while others might be almost empty, vast cosmic voids. We can never directly detect these differences because the light from those regions can never reach us, but their existence could deeply affect our understanding of the universe as a whole. One of the most fascinating and speculative ideas about what lies beyond the observable universe is the concept of a multiverse. Some interpretations of cosmology, particularly those involving inflationary theory, suggest that the universe we see might be just one of many pocket universes or bubbles that formed during the earliest moments of cosmic inflation. During this period, space expanded at an incredible rate, creating separate regions of space-time, each with its own distinct properties. Our observable universe would be just one of these regions, while others lie forever beyond our reach. These other universes could be dramatically different from our own, with different physical laws, different constants, or even more dimensions than the three of space and one of time that we are familiar with. The multiverse idea paints a vision of a cosmos far grander and stranger than anything we experience, where entire universes exist beyond the horizon, each with its own rules and structures. While this idea is difficult, if not impossible, to test directly, it offers a breathtaking perspective on what might exist beyond the limits of our observation. Even if we assume that the universe beyond the horizon is much like the one we can see, the expansion of space still plays a crucial role in shaping those distant regions. As space continues to stretch, galaxies beyond the horizon move farther away, and the distances between them grow. The cosmic expansion works the same way there as it does in the regions we can observe. Over immense spans of time, these distant parts of the universe may become increasingly disconnected from our observable universe. If the expansion of the universe continues to accelerate, driven by dark energy, more and more regions of space could move beyond the reach of light, effectively isolating pockets of galaxies from one another. In such a future, the universe could become a vast, fragmented place, with enormous empty stretches separating isolated clusters of matter. For observers in those faraway regions, the universe would appear small, isolated, and far less connected than the universe we experience today. The idea of the cosmological horizon raises profound questions about space itself. Is space infinite, or is it expanding into something else? This question goes beyond the simple observation that galaxies are moving apart and touches on the very nature of reality. If the universe is infinite, it has no edge, no boundary, and no limit. It simply stretches on forever in all directions. In this case, the expansion of the universe means that even though space is boundless, the distances between objects continue to grow endlessly. The concept of an infinite universe is hard for us to grasp because we are used to thinking about things with edges or limits, yet here there is no outer boundary at all. Some theories propose that the universe might be finite but unbounded. This means that the universe has a certain size, yet there is no edge you could reach. Imagine the surface of a balloon. It has a limited area, but you could travel in one direction forever without ever encountering a boundary, eventually returning to where you started. Similarly, the universe might have a finite volume yet no edges, creating a cosmic landscape that loops back on itself. Others wonder whether the universe could be expanding into something else. In everyday life, when we think of expansion, we imagine objects spreading into pre-existing space. But the universe is different. Space itself is expanding. It is not moving into some larger container, because space and time are part of the universe itself. If there is something beyond the universe, it does not affect the expansion we observe. Even if our universe is one bubble in a multiverse, the stretching of space we see happens within our universe alone. What lies beyond, if anything, remains one of the greatest mysteries of science. At the tiniest scales, the fabric of space is far from smooth. According to quantum theory, space at the smallest levels is a frothing, restless landscape known as quantum foam. Here, energy fluctuates constantly, and particles appear and vanish in mere fractions of a second. In this quantum realm, space is unpredictable and lively, a far cry from the smooth and continuous space we experience in everyday life. Could the universe be infinite on large scales but fundamentally granular or discrete at the smallest scales? If so, the very idea of infinite space becomes even more complex. While cosmic expansion shapes vast regions of the universe, quantum mechanics dominates the smallest scales. Some scientists speculate whether these two extremes might be connected. Could the expansion of space itself be influenced by the restless fluctuations of the quantum foam? This remains an area of active research, as scientists strive to link the enormous scales of cosmic expansion with the tiny, invisible scales of quantum mechanics, hoping to uncover a deeper understanding of the universe in all its vastness and complexity. Curvature is a concept that lies at the very heart of our understanding of the cosmos, shaping the very structure of the universe and intimately connected with the way it grows and evolves over time. From the smallest scales of stars and planets to the vast cosmic web stretching across billions of light years, the bending or warping of space plays a fundamental role in determining how matter and energy behave, and how galaxies, clusters, and superclusters of galaxies move through space. The question of what the universe looks like on the grandest scales, whether it curves back on itself, spreads endlessly, or remains essentially flat, has been a central mystery for generations of astronomers, cosmologists, and physicists. Scientists have long debated the shape of the universe, and over the decades, three broad possibilities have emerged for its overall curvature. The universe could be flat, it could be closed, or it could be open. Each of these possibilities describes a different geometric nature of space itself, and while it is challenging to visualize these concepts with the mind alone, they have very real consequences for the way the cosmos behaves, for the journey of a light from distant galaxies, for the fate of stars and galaxies, and for the ultimate destiny of all matter and energy. The notion of curved space comes from the revolutionary ideas introduced by Albert Einstein in the early 20th century through his theory of general relativity. Einstein proposed that mass and energy are not merely passive inhabitants of space, but active shapers of it. Massive objects such as stars, planets, and entire galaxies do not simply sit in space. They bend and warp the fabric of space itself around them. This warping is what we perceive as the force of gravity. For example, the Sun, by virtue of its enormous mass, creates a curvature in the surrounding space that dictates the orbits of the planets in our solar system, keeping Earth and the other planets in stable paths around it. This curvature is relatively slight when we examine local regions like our solar system or even our Milky Way galaxy. Yet when considered across the universe as a whole, the total distribution of mass and energy can shape the universe's global curvature in profound ways. On the larger scales, the curvature of the universe can be thought of in three simplified forms: flat, closed, or open. Each of these geometric possibilities carries a distinct set of implications for the cosmos and its expansion. In a flat universe, space extends uniformly in every direction without curving back on itself. It is a geometry much like that of a vast, limitless sheet of paper. In such a universe, parallel lines would remain parallel forever, never converging or diverging, and the sum of the angles in any triangle, no matter how large, would always add up to exactly 180 degrees. A flat universe implies a precise balance of mass and energy, enough to prevent the cosmos from collapsing under its own gravity, but not so much that it will halt its expansion entirely. In this scenario, the universe expands, but the expansion slows gradually over time due to the mutual gravitational attraction of all matter. By contrast, a closed universe is akin to the surface of a sphere, a three-dimensional analogue of a two-dimensional globe. In a closed cosmos, space curves back on itself, forming a finite but unbounded structure. Imagine travelling in a straight line across the surface of a perfectly spherical planet. Eventually, you would arrive back where you started, having circled the entire surface. Similarly, in a closed universe, if one could move in a straight path for an unimaginably long distance, it is theoretically possible to return to one's starting point. The total mass and energy in a closed universe is sufficient to generate a strong gravitational pull that will ultimately overcome the expansion of space. While the universe may currently be stretching outward, in a closed scenario this expansion is temporary. Over vast spans of time, the gravitational tug of all the mass and energy would slow the expansion, eventually stopping it altogether and then reverse it, causing the cosmos to contract. This contraction would continue inexorably, culminating in a scenario often called the Big Crunch, in which all matter and energy collapse back into an extremely dense hot state, reminiscent of the universe at its earliest moments. On the other end of the spectrum lies an open universe, which is characterized by a negative curvature similar to the shape of a saddle. In this scenario, space curves away from itself rather than back on itself, creating a geometry that diverges rather than loops. If one were to travel in a straight line in an open universe, there would be no returning to the starting point. The journey could continue endlessly without looping back. In an open cosmos, the total amount of mass and energy is insufficient to halt the expansion. Gravity is simply too weak to pull everything back together. As a result, the universe would continue to expand forever, with galaxies moving ever farther apart. The farther apart galaxies are, the faster they would drift away from each other, a phenomenon amplified by the continual stretching of space itself. In an open universe, the angles of a triangle would add up to less than 180 degrees, and lines that start off parallel would slowly diverge over vast distances. To summarize the implications of these three possibilities in more practical terms, in a flat universe the expansion of space would gradually slow, moderated by the gravitational pull of the universe's own mass. In a closed universe, expansion would reach a maximum, then reverse, eventually bringing about a collapse of all cosmic structures. In an open universe, expansion would continue indefinitely, but the rate of expansion could gradually slow as matter exerts a diminishing pull over ever-increasing distances. Each of these scenarios represents a profoundly different vision of the universe's fate, influenced entirely by the overall curvature dictated by the total mass and energy contained within the cosmos. One of the most important tools that cosmologists use to explore the shape of the universe is the cosmic microwave background, often abbreviated as CMB. This faint radiation is a relic from a time roughly 380,000 years after the Big Bang, when the universe had cooled enough for light to travel freely through space. By studying the minute variations in temperature and density imprinted on the CMB, scientists can measure the curvature of space on scales spanning billions of light years. These observations provide crucial evidence about the large-scale geometry of the universe. To the surprise of many researchers, these measurements indicate that the universe is remarkably flat. In other words, on the larger scales that we can observe, space does not curve in any detectable way. This does not imply that space is perfectly flat in an absolute sense, but rather that any curvature it might possess is extremely small, so subtle that our current instruments cannot measure it. However, even if the universe is flat on cosmic scales, this does not mean that its expansion will proceed at a steady, unchanging rate indefinitely. A major twist in our understanding of cosmic evolution came with the discovery of dark energy, an invisible form of energy that permeates all of space and acts as a kind of anti-gravity, driving the expansion of the universe to accelerate rather than slow. Dark energy fundamentally alters the destiny of the universe. Even in a flat cosmos, the presence of dark energy can cause galaxies to move away from each other ever more rapidly over time, stretching space itself at an accelerating pace. This means that the simple geometric classification of the universe as flat, open, or closed, while critical for understanding large-scale structure, does not alone determine the ultimate behavior of cosmic expansion in a universe dominated by dark energy. The apparent flatness of the universe also raises a profound question. How did the universe end up in such a finely balanced state? A flat universe requires a very precise ratio of mass and energy, such that any small deviation in the early cosmos would have produced a universe that was either open or closed. The probability of the universe naturally arriving at this exact balance seemed incredibly small, and this puzzling fine-tuning led to the development of the theory of cosmic inflation. According to inflationary theory, in the earliest moments after the Big Bang, the universe underwent an extraordinarily rapid expansion, growing exponentially in size in a fraction of a second. This sudden stretching smoothed out any initial irregularities or curvature, effectively flattening the cosmos on large scales. Just as stretching a wrinkled sheet of fabric flattens it, cosmic inflation could have eliminated significant curvature, leaving the universe remarkably flat as we observe it today. Yet, despite the universe appearing flat on vast scales, the effects of curvature are very much real and present in the immediate vicinity of massive objects. Within galaxies and clusters of galaxies, the warping of space caused by gravity is directly observable. Stars orbit galactic centers because of the curvature of space around massive black holes and dense regions of mass. Light from distant objects bends as it passes near massive bodies, producing phenomena known as gravitational lensing, which can magnify or distort the images of faraway galaxies. Planets follow curved orbits around their stars not because they are being pulled through a void, but because the space around them is curved by the mass of the star. This local curvature, while highly significant for astrophysics, does not dictate the overall expansion of the universe in the same way that large-scale curvature does. It is also possible that the universe possesses a slight curvature that remains below the threshold of our current observational capabilities. If the cosmos is only very slightly closed or slightly open, the effects would manifest only over incomprehensibly large distances, far beyond the regions we can currently measure. Future improvements in telescopes, satellites, and measurement techniques may eventually reveal tiny deviations from flatness, giving us a more nuanced picture of the universe's geometry. Even minute curvature could influence the long-term evolution of the cosmos, subtly shaping the motion of distant galaxies and affecting the propagation of light over billions of light years. The study of the universe's curvature is thus intertwined with nearly every aspect of cosmology and astrophysics. It connects the theoretical predictions of Einstein's general relativity with observable phenomena such as the distribution of galaxies, the patterns imprinted in the cosmic microwave background, the gravitational lensing of distant light, and the behavior of the universe's expansion over billions of years, the concept of curvature provides a bridge between the local warping of space that governs planetary orbits and the global geometry that dictates the ultimate fate of all cosmic structures. It is a lens through which we can understand the relationship between mass, energy, space, and time. Curvature also influences the apparent distance between galaxies and the way astronomers measure cosmic expansion. For example, if the universe were closed, light travelling from a distant galaxy would eventually traverse a curved path, affecting how we perceive the galaxy's position and motion. In an open universe, the divergence of space would stretch light waves, impacting the observed redshift and the apparent brightness of distant objects. Even in a flat universe where space does not curve in a detectable way, the sheer scale of cosmic distances means that curvature, however slight, plays a role in refining our measurements and our understanding of cosmic history. The dynamics of expansion are further complicated by the interplay between curvature, gravity, and dark energy. In the earlier stages of cosmic history, gravity dominated, slowing the expansion in proportion to the mass and energy present. In a closed universe, this slowing would eventually lead to contraction, while in an open universe, expansion would continue but with diminishing acceleration. The discovery of dark energy revealed that expansion is not merely a consequence of initial conditions and gravitational pull, but is actively driven by a mysterious force that accelerates space itself. This acceleration, observed in the late 20th century through careful measurements of distant supernovae, demonstrates that the universe's expansion is not just a slowing after effect of the Big Bang, but a dynamic process influenced by unseen energy permeating all of space. Cosmic inflation, local gravitational effects, the total mass and energy density, and dark energy all interact to determine the observable properties of the universe. The remarkable flatness observed in current measurements suggests a delicate balance between these factors, a balance that may hold clues to the underlying mechanisms governing the cosmos. Even the smallest deviations from perfect flatness can provide insights into the earliest moments after the Big Bang, revealing the nature of inflation, the distribution of matter, and the role of dark energy in shaping cosmic evolution. The curvature of the universe, while abstract and difficult to visualize, has tangible consequences for our understanding of time, space, and motion on the grander scales. It frames the questions we ask about the fate of galaxies, the propagation of light, and the ultimate structure of the cosmos. It links the local physics of stars and planets to the cosmic tapestry stretching across billions of light years, showing that the same principles governing the motion of a single planet also shape the destiny of entire galaxy clusters. Curvature is not merely a theoretical construct. It is an observable reality, imprinted on the very fabric of space, influencing how matter moves, how light travels, and how the universe grows and evolves. In addition, the concept of curvature opens the door to philosophical and scientific contemplation about the very nature of space and time. What does it mean for the universe to be flat, closed, or open? How do these abstract geometric properties translate into the lived reality of galaxies, stars, and planets? How did the early universe achieve such remarkable flatness, and what hidden forces or processes might remain undiscovered that shaped its geometry? The interplay between curvature, gravity, dark energy, and expansion provides a continuous source of inquiry and investigation, guiding generations of scientists as they refine measurements, improve observational techniques, and develop more sophisticated models of cosmic evolution. Local measurements of curvature, such as those made within our galaxy or through the observation of gravitational lensing, confirm that mass and energy do warp space in tangible ways. Yet these local effects do not determine the ultimate shape of the universe on the larger scales, which is dictated by the total density of mass and energy, and the initial conditions set by the Big Bang and subsequent inflation. The flatness revealed by observations of the cosmic microwave background suggests a cosmos balance between gravitational collapse and runaway expansion, a balance so precise that even slight deviations would have produced an entirely different universe. This fine-tuning, and the mechanisms that might have produced it, remain at the cutting edge of cosmological research. As technology advances, the limits of our observations will continue to expand, allowing for more precise measurements of cosmic curvature. Future telescopes, satellites, and detectors may uncover subtle deviations from flatness, revealing whether the universe has a slight positive curvature or a small negative curvature that has so far eluded detection. Such findings could deepen our understanding of dark energy, inflation, and the fundamental forces that govern cosmic evolution. Each new measurement, each refinement in technique, brings humanity closer to grasping the true shape of the cosmos and how it evolves across the incomprehensible vastness of space and time. Even in a universe that is predominantly flat, the effects of curvature cannot be entirely ignored. Gravity continues to warp space on small and intermediate scales, shaping the motion of stars within galaxies, guiding the paths of comets through solar systems, and bending the trajectories of light from distant objects. Meanwhile, on cosmological scales, the geometry of space influences the propagation of light, the separation of galaxies, and the ultimate patterns imprinted on the cosmic microwave background. Curvature is thus a concept that bridges the local and the cosmic, linking the behavior of matter and energy on human scales to the destiny of the universe itself. In the context of the ongoing expansion, the universe's curvature interacts with the mysterious influence of dark energy to determine the rate at which space stretches. Even a flat universe, under the influence of dark energy, can experience acceleration in expansion that surpasses the expectations based solely on mass and gravity. Observations of distant galaxies show that not only is the universe expanding, but that the rate of expansion has increased over the last several billion years. This acceleration, influenced by the interplay between dark energy and cosmic geometry, demonstrates that the universe is far from static, that space itself is a dynamic entity, and that curvature, while subtle, remains an essential element in understanding the cosmos. As the universe keeps getting bigger and bigger, the huge structures that make up its shape are also changing. These massive structures, like groups of galaxies, long threads of matter, and giant empty spaces called voids, didn't just appear by chance. They were formed over billions of years as gravity slowly pulled matter together, creating enormous networks where galaxies are connected by invisible threads of both dark matter and the regular matter we know. But while gravity pulls galaxies toward each other, something else is pushing them apart: the steady growth of space itself. This creates a kind of cosmic tug-of-war. On one side is gravity, always trying to gather things together, and on the other side is expansion, stretching the universe and pushing galaxies farther and farther apart. Over time, this expansion is creating bigger gaps between galaxies and cosmic structures. It's stretching the very fabric of the universe, changing its shape on the largest scales possible. Scientists call the overall shape of the universe the cosmic web. Imagine a giant three-dimensional spider web made up of galaxies. The threads of this web are called filaments, long lines filled with galaxies. These filaments connect bigger groups of galaxies called galaxy clusters. Between all of these structures are huge empty spaces called voids, areas where very few galaxies exist at all. However, the universe's expansion doesn't happen the same way everywhere. Inside galaxy clusters, gravity is strong enough to keep galaxies close together. So even as space stretches, these galaxies stay bound to each other. But in the huge spaces between the clusters, gravity isn't strong enough to hold things together. There, space keeps growing, causing the voids to get larger and the filaments to stretch thinner over time. This leads to a process called cosmic drift. It means that galaxies that were once near each other slowly move apart. Long ago, in the early days of the universe, galaxies often collided and merged. These collisions helped shape the galaxies we see today, but now those kinds of encounters are happening less often. As galaxies become more isolated, they can no longer easily share gas, dust, or stars. The universe is becoming quieter and calmer. One of the most noticeable changes caused by this expansion is the growth of the voids. These vast empty areas are getting even bigger. As a result, the overall structure of the universe is spreading out and breaking into pieces. In the very distant future, the universe might look like a dark, quiet ocean with small glowing islands scattered across it. These islands being the galaxy clusters. Even though space is expanding, the galaxies inside each cluster will probably stay close together because their gravity is strong enough to keep them in place. But outside those clusters, nothing can stop the universe from stretching. Right now, galaxy clusters are still connected by filaments, but these links are weakening. One day, the threads will stretch so far that they break, and the galaxies in the filaments will drift away from each other. Eventually, each cluster will become isolated, surrounded by ever-growing voids. From any single galaxy, only the few nearby galaxies in the same cluster will be visible. All the others, spread far away, will disappear from view, not because they vanish, but because their light will be stretched so much by the expansion of space that it won't be detectable. Scientists call this redshifting, and in extreme cases it pushes light into invisible forms. This means that, in the future, the observable universe, the part we can actually see, will shrink. Not in size, but in the number of galaxies we can see from any place. For future astronomers, it will feel like living in a small bubble of stars, with the rest of the universe hidden behind a cosmic curtain. As this happens, many of the processes that once shaped galaxies, like merging, forming new stars, or sharing gas and dust, will slow down. In the early universe, galaxies were born from clouds of gas and dark matter that collapsed under their own gravity. But as the universe expands and spreads everything out, there is less material to work with. The matter becomes so thin that making new galaxies becomes almost impossible. Existing galaxies will keep changing slowly, but the creation of brand new galaxies from ancient gas clouds will eventually stop. One day, the universe may reach a point where no new galaxies form at all. The galaxies that already exist will keep drifting away from each other until even their light can no longer cross the huge empty spaces between them. The result will be a universe that is darker, quieter, and lonelier than ever before. Now, all this talk about expanding space raises another interesting question. Could the stretching of space affect how we experience time? Time and space are not completely separate. According to Einstein's theory of general relativity, they are two parts of the same thing, space-time. This means that when space stretches, bends, or changes, time can be affected too. For example, when space bends around something massive like a star or black hole, time slows down nearby. This has been proven by experiments. So, if the universe itself is expanding, does that mean time is changing too? The simple answer is, not in a way we can easily notice. On Earth, time seems to pass the same as always. Our clocks tick steadily. The Earth still orbits the Sun once every year. Sunrises and sunsets happen on schedule. In our daily lives, cosmic expansion doesn't seem to change time at all. But on the larger scales, across galaxies and the entire universe, space and time are closely connected. In our daily lives, we don't feel the effects of the universe's expansion. Everything around us, our homes, trees, the Earth, and even the Sun, feel stable. That's because on small scales, like inside our solar system, or even inside galaxies, a strong force called gravity dominates. Gravity pulls objects together and stops them from drifting apart. It keeps planets in orbit, holds stars together, and binds entire galaxies into huge spinning systems. So, even though the universe is expanding, we don't notice it here because gravity is stronger than the gentle stretching of space in our local area. Time also works normally in these small areas. We don't see it slow down or speed up dramatically. But when we look at much larger distances, across millions or even billions of light years, things start to change in amazing ways. In the huge spaces between distant galaxies, where gravity is weak and expansion is stronger, the stretching of space actually affects both light and time. As space expands, it stretches the light travelling through it. This stretching causes what scientists call a redshift. Imagine light waves like ripples in a pond. When the pond stretches, the ripples get longer and slower. That's what happens to light coming from faraway galaxies. It gets stretched out and shifts to the red end of the spectrum, which has longer waves. But this redshift doesn't just make light look redder. It also changes how we experience time from those galaxies. The farther away a galaxy is, the more stretched its light becomes, and the slower that light seems to reach us. It's almost like time itself is moving more slowly in those faraway places. When we look at a supernova, an exploding star, billions of light years away, we see it in slow motion. Its explosion happens more slowly than it would if it happened nearby. This strange effect is called time dilation, and it happens because the universe is expanding. In fact, when we look at the far edges of the observable universe, we're not just looking across space, we're also looking far back in time. But because the universe is expanding, That ancient time seems to pass very slowly. The expansion of space stretches both the light waves and the actual duration of events. A cosmic event that might last a few seconds nearby could seem to take much longer if it happened billions of light years away. Some scientists think that as the universe keeps expanding faster and faster, time itself could eventually be affected in even stranger ways. One idea is that the universe could end in what's called the Big Freeze or heat death. In this scenario, all the stars will burn out, galaxies will drift apart, and the universe will become cold and dark. With no stars or energy left, time might lose its meaning completely. If nothing is changing and no events happen, then there's nothing left to measure time by. Time itself could stop. According to Einstein's theory of general relativity, time isn't a fixed thing like a ticking clock. Instead, time is relative. It moves at different speeds depending on gravity and motion. For example, near a massive object like a black hole, time slows down. This is called gravitational time dilation. Scientists have even proven this by placing very precise clocks on airplanes and satellites. The clocks tick a little more slowly in stronger gravity. Some scientists have begun to ask a question that might seem almost impossible to imagine. What if time, the thing we measure with clocks and calendars, is not something basic or fundamental at all? What if time is not a built-in part of the universe, but instead something that appears because of deeper hidden processes? Perhaps it emerges from the way space, matter, and energy interact with each other. This is still just a theory, a fascinating idea that has not yet been proven. But it opens up a world of possibilities about what time really is and how it works. Now let's think about another curious question. The universe is expanding, stretching space itself, but does this stretching affect the tiniest parts of the universe? What happens at the quantum level, the realm of particles such as electrons, protons, and neutrons, where the rules of physics are very different from the world we see every day? At its simplest, the expansion of the universe means that the space between galaxies and clusters of galaxies is growing larger and larger over time. However, inside galaxies, and even more so inside stars, planets, and atoms, the expansion of space doesn't really have any effect. The forces that hold these smaller structures together are far stronger than the gentle push of cosmic expansion. Take atoms, for example. Inside each atom, tiny particles are held tightly together by incredibly powerful forces. The electromagnetic force keeps electrons moving around the nucleus, while the strong nuclear force binds the nucleus itself, preventing it from falling apart. The strong nuclear force is roughly 100 times stronger than electromagnetism, and millions of times stronger than gravity. These forces are so powerful that they keep the very building blocks of matter intact. Because of this, the atoms in your body are not stretching. The molecules in the air are not drifting away from one another. The rocks beneath your feet remain solid. Even entire planets and stars do not feel the universe expanding. The expansion only becomes noticeable in the enormous, mostly empty regions between galaxies, where there is very little matter to resist the stretching. This contrast shows just how dominant the small-scale forces are in our daily world. They easily overpower the weak, subtle push of cosmic expansion. For everything we see, touch, and live among, the fundamental forces hold everything tightly together. Yet scientists continue to wonder, could the expansion of the universe have any effect at all in the quantum world, the realm of the very tiny? At first glance, the answer seems simple. Not really. The cosmic expansion and quantum mechanics appear to operate on completely different scales. But when scientists look closer, they discover some truly fascinating links that suggest the two may be connected in ways we are only beginning to understand. These links take us into some of the strangest, most mysterious areas of physics. One of these links comes from something called quantum fluctuations. According to quantum theory, the set of rules that governs the tiniest scales of nature, even smaller than atoms, empty space is not truly empty. Instead, it is full of restless energy. In this restless vacuum, tiny particles can suddenly appear and vanish in an instant, like sparks flashing on and off in the darkness. These strange events are happening all the time, but they are so small and fleeting that we do not notice them in our everyday lives. Some scientists believe that these tiny quantum fluctuations played a critical role in shaping our universe. Around 13,800,000,000 years ago, shortly after the universe was born, it went through a remarkable period known as cosmic inflation. During this extraordinary moment, which lasted only a fraction of a second, the universe expanded at an almost unimaginable speed, faster than the speed of light. In less time than it takes to blink your eye, space grew from something smaller than a single atom to a size far larger, perhaps even reaching scales large enough to encompass galaxies. Here is where it becomes truly fascinating. Those tiny quantum fluctuations were also stretched as space expanded. The microscopic ripples in energy grew along with the universe. Over billions of years, these minuscule variations became the seeds that eventually formed galaxies, stars, and all the vast structures we see in the cosmos today. In this sense, the enormous universe we observe may have its origins in the hidden, mysterious quantum world, a place so small that we cannot see it directly. Another intriguing connection between cosmic expansion and quantum theory involves dark energy, the mysterious force believed to be driving the universe to expand faster and faster. Some scientists even suggest that dark energy itself could arise from the quantum realm. If this is true, then the growth of space across the universe may be deeply linked to the behavior of the tiniest particles, connecting the largest and smallest scales of reality in ways we're only beginning to glimpse. The universe, from its smallest quantum ripples to its vast galactic clusters, may be far more interconnected than we have ever imagined, a reminder that even the tiniest sparks of energy can shape the cosmos on a grand scale. For many decades, scientists have been pondering what the endless expansion of the universe might mean for its far, far future. One of the most famous ideas that keeps coming up is called the heat death of the universe. Despite its dramatic name, it is not a violent explosion or an abrupt ending. Instead, it is more like a quiet, slow fading. A universe gradually losing its spark and drifting into stillness. The heat death theory suggests that if the universe continues to expand forever, there will come a time when all energy is spread out evenly across the cosmos. When this happens, no energy differences will remain, and without energy differences, nothing can do any work. Stars will no longer shine, planets will no longer orbit, galaxies will no longer form, and nothing new will happen anywhere. Everything will simply come to a gentle, eternal stop. Scientists sometimes call this final, frozen state the Big Freeze. To understand this, we need to talk about a concept called entropy. Entropy, in simple terms, means disorder or randomness. In our everyday lives, we can see entropy all around us. A tidy room slowly becomes messy. A hot cup of tea gradually cools down. Over time, things naturally move from order to disorder. In the universe, the same idea applies. Entropy always increases. As time goes on, energy spreads out more and more. Imagine the energy from a shining star. It is strong, focused, and full of potential. But as the universe expands, that energy is stretched thinner and thinner, like a drop of ink diluted in an ever-growing ocean. It becomes weaker, less able to light up new stars or fuel cosmic activity. This spreading out of energy is one of the clearest signs that entropy is rising. Over unimaginably long periods, billions, then trillions of years, stars will burn through all their fuel. Some will collapse into black holes, others will fade into cold, dim white dwarfs, and many will erupt in spectacular supernova explosions. Eventually, no new stars will form at all. The surviving stars and their remnants will slowly grow cold and dark, leaving only the faintest traces of their former brilliance. Our own galaxy, the Milky Way, might one day collide and merge with nearby galaxies in a cosmic dance within a group known as the local group. Meanwhile, galaxies far beyond this cluster will vanish from view. They will move away from us faster than the speed of light, driven apart by the universe's continuing expansion. After a very long time, only tiny islands of matter will remain, floating in a vast sea of emptiness. The last sources of energy in this distant future will be incredibly weak. There will be a faint leftover glow from the Big Bang, the ancient flash of creation itself. Occasionally, tiny sparks may flicker as black holes slowly decay. Even black holes, which we often think of as eternal, will not survive forever. A famous scientist named Stephen Hawking predicted a strange effect, now called Hawking radiation, which suggests that black holes gradually lose mass by emitting tiny amounts of energy. Over unimaginably long spans of time, periods so vast that our minds can barely grasp them, even the largest black holes will evaporate, vanishing entirely into nothingness. Once all black holes are gone, and matter itself has broken down into its smallest components, the universe will become an utterly dark, cold, and silent place. It will be filled with a thin haze of low-energy particles drifting endlessly through ever-expanding space. No stars, no galaxies, no movement, no change, just a silent, frozen emptiness. At this point, the universe will have reached maximum entropy. This means there will be no differences in energy anywhere. Without energy differences, nothing can happen. No chemical reactions, no light, not even the subtle motion of atoms. In this lifeless state, the universe will be, for all practical purposes, completely dead. This vision of the distant future, the heat death of the universe, is based on our current understanding of physics, including the expansion of space, the mysterious force called dark energy, and the rules of thermodynamics, which govern how energy behaves. If the universe keeps expanding forever, and if dark energy continues to act as it does today, the heat death scenario becomes a very real possibility. But science is always evolving. Future discoveries could reveal a completely different fate for the cosmos. We still know very little about the true nature of dark energy and the deeper workings of the universe. What we do know is that dark energy plays a major role in this slow march toward heat death. If it continues to dominate, it will prevent new stars and galaxies from forming, leaving the universe colder and emptier with each passing epoch. Although this picture might seem bleak, it is important to remember just how unimaginably far in the future we're talking about. These changes will not occur for trillions upon trillions of years, numbers so enormous they are almost impossible to imagine. Right now, the universe is still lively and active. Stars are being born in vast clouds of gas. Galaxies are still colliding and merging in spectacular cosmic dances. Life is thriving, at least on one small blue planet we call Earth. The heat death represents a vision of the very distant future, far beyond the life of our planet, our solar system, or even our galaxy. It is one possible ending for the universe based on what we know today. Yet the cosmos may still hold secrets and surprises we have not yet discovered, leaving room for new possibilities in the endless story of space and time. The idea that the universe could keep expanding forever is already strange and hard to picture. But there is an even more dramatic and frightening possibility, one that scientists call the Big Rip. Unlike the gentle, quiet fading of everything imagined in the heat death scenario, where the universe slowly grows cold and energy spreads thinly across unimaginable stretches of time, the Big Rip is violent, sudden, and terrifying. Instead of gradually cooling down, the universe could eventually be ripped apart piece by piece until not a single atom remains. But how could such a shocking fate begin? It starts with something we already know. The universe is expanding, and not only that, it is expanding faster and faster with time. This accelerating growth is mostly driven by a mysterious force known as dark energy, a strange, invisible presence that pushes galaxies away from each other, stretching the fabric of space itself. Right now, dark energy seems relatively gentle, slowly pulling galaxies apart. But some scientists suspect that in the far future, it might grow far stronger. According to the Big Rip idea, dark energy could gradually gain strength as time passes. If that happens, it could become so powerful that it would overwhelm all the forces that hold matter together. Gravity, which keeps stars in galaxies, electromagnetism, which binds atoms, even the strong force which holds atomic nuclei intact, all could be defeated by this unstoppable force. Here is how the Big Rip might unfold step by step. First, on the larger scales, galaxy clusters, enormous collections of galaxies bound together by gravity, would start to separate from each other faster than the speed of light. Entire regions of the universe would become forever cut off, unable to send light, information, or travel to one another. Next, as the expansion continues to accelerate, individual galaxies themselves would begin to fall apart. The gravitational pull that keeps stars orbiting around galactic centers would no longer be strong enough. Stars would drift away in all directions, scattered across the growing emptiness of space. But the destruction does not stop there. As time goes on and expansion grows even more extreme, solar systems like our own would be torn apart. planets would be ripped from the stars they circle. Even if a planet like Earth somehow survived the earlier stages, it would not survive this one. Every planet, every moon, every asteroid would be flung into the stretching void, lost to the cosmic tide. Then comes the most terrifying stage. Eventually, dark energy could grow so powerful that it would tear apart the very building blocks of matter. Atoms themselves would be destroyed. Electrons orbiting atomic nuclei would be ripped away by the force of expansion. The electromagnetic force, one of the four fundamental forces of nature, would no longer be able to hold them together. Matter itself would cease to exist in any recognizable form. In the final moments, nothing would be safe, not even space and time itself. The laws of physics, which have always governed the behavior of particles and energy, would break down completely. The universe would tear apart at a speed beyond human comprehension, leaving only scattered particles drifting in an endlessly expanding emptiness. And here is what makes this possibility even more unsettling. It would not take forever. If conditions were just right, this horrifying end could arrive in as little as 22 billion years from now. That may sound like an unimaginably long time, but in cosmic terms it is short, especially when compared to the trillions of years expected for a slow, quiet heat death. A key idea behind the Big Rip is that dark energy might not stay the same forever. At present it seems steady, with a consistent effect on the universe's expansion. But some scientists suggest it could strengthen over time. If so, the Big Rip could truly happen. On the other hand, if dark energy remains constant, as most current models predict, then a Big Rip is unlikely. Instead, the universe will drift toward a slow, frozen heat death, gradually fading into cold, silent stillness over mind-boggling stretches of time. Astronomers and physicists are working to unravel this cosmic mystery by studying faraway galaxies and brilliant exploding stars known as supernovae. Their observations have already confirmed that the universe is not just expanding but accelerating. However, determining whether the Big Rip will actually occur requires far more precise measurements of dark energy and its behavior over billions of years. Until then, we are left to imagine two vastly different futures, one in which the universe fades into quiet, icy emptiness over trillions of years, and another in which it violently tears itself apart in a dramatic cosmic catastrophe just 22 billion years from now. As our universe keeps stretching and growing, one of the most exciting things to think about is the role that black holes might have in this huge cosmic story. These strange objects, with gravity so strong that nothing, not even light, can escape them, could be very important for understanding how the universe might change in the far, far future. They might even hold the key to survival for any advanced civilizations that still exist at that distant time. First, black holes don't just stay the same over time. They actually change. They can grow bigger by swallowing nearby matter, like gas, stars, or even other black holes. When two black holes crash into each other, they merge and form one bigger black hole. But here's the thing. As the universe keeps expanding and galaxies drift farther and farther apart, it becomes harder for black holes to find anything to eat. The space between galaxies keeps getting larger, making the universe more empty and lonely. Eventually, black holes may end up in a universe where there is almost nothing left to feed on. The big structures, like galaxies and clusters of galaxies, that once gave them material will become isolated. Without new material falling in, black holes will stop growing and remain as quiet, dark objects floating in a universe that keeps getting colder. Over time, the universe will become colder and emptier, with fewer and fewer particles. Stars will burn out, galaxies will fade, and black holes will become the last powerful objects in the cosmos. Even though everything else may disappear, black holes are made to last. While stars shine brightly for a few billion years before burning out, black holes, especially the huge ones called supermassive black holes, can survive for unimaginably long times. These supermassive black holes sit at the centers of galaxies, including our own Milky Way, and they might still be around when everything else is gone. But even black holes are not forever. A famous scientist named Stephen Hawking suggested that black holes slowly lose mass over time by giving off a tiny bit of energy called Hawking radiation. This means that, given enough time, black holes will shrink and eventually disappear. But don't worry, this happens very slowly. For the biggest black holes, it might take trillions upon trillions of years. Still, this idea fits well with one possible ending for the universe called the heat death. In that ending, energy becomes so spread out that nothing can happen anymore. No heat, no light, no life. Yet before everything fades into that final darkness, black holes might be a last hope for survival. If there are any intelligent civilizations left billions or trillions of years from now, they might rely on black holes as one of the few remaining sources of usable energy. Since stars will be dying out and other energy sources will vanish, black holes might become cosmic batteries. One interesting idea is called the Penrose process. This idea says that it might be possible to drop objects into the swirling area just outside a spinning black hole. If done right, this could let a civilization take energy from the black hole's rotation. It's like taking energy from a spinning wheel, only on an unimaginable scale. Even in an aging universe, this could give civilizations enough power to survive. Another source of energy comes from the accretion disks around black holes. These are glowing rings of gas and dust that spin around black holes, getting extremely hot as they fall inwards. The process releases huge amounts of energy. Some black holes may still have these glowing disks for a very long time, pulling in whatever material is left nearby. Advanced civilizations could build machines to collect this energy and stay alive much longer, even as the universe grows darker and colder. But black holes might offer more than just energy. They could also help civilizations stretch out their time. Some scientists have imagined that intelligent beings could build structures close to a black hole, where gravity is so strong that time slows down compared to the rest of the universe. This is called time dilation, and it means that time would move more slowly for someone near the black hole than for someone far away. In theory, this could let civilizations experience millions of years as if only a short time had passed. In a universe running out of time and energy, this could be a powerful way to delay the end. So, as the universe keeps expanding and becomes more and more empty, black holes might be the last safe places, spots where energy, life, and complexity might still exist. Everything else, stars, planets, and galaxies, will slowly vanish. But black holes, with their strange powers and strong gravity, could be the last beacons in a fading universe. Whether they are used to power the final civilizations or simply remain as ancient relics from a livelier cosmos, black holes will likely play an important role in the final chapter of the universe's story. To really understand these possibilities, we need better ways to watch and study the universe. The tools we use today, like modern telescopes, have already shown us amazing things. But to answer the big questions about the future of black holes, the end of the universe, and everything in between, we need even more advanced technology. Thankfully, scientists and engineers are working hard to build the next generation of space telescopes and observatories. These tools will help us see deeper into space and further back in time than ever before. One of the most exciting of these is the James Webb Space Telescope, often called JWST. It was built to follow in the footsteps of the famous Hubble Space Telescope. Hubble gave us breathtaking pictures and taught us a lot, especially about the redshift of galaxies, how the light from faraway galaxies stretches as the universe grows. But JWST is even stronger. It can see infrared light, which lets it look even farther into the past. As the universe expands, light from the earliest galaxies becomes stretched into longer, redder waves. JWST is made to detect this stretched light, helping scientists study galaxies that formed just a few 100 million years after the Big Bang. By watching these early galaxies, scientists can learn how the universe began to grow and how that growth changed over time. With tools like JWST, we get closer to solving the mysteries of black holes, cosmic growth, and the ultimate fate of the universe. The European Space Agency, or ESA, is helping a lot in understanding how the universe grows. One of its big projects is a space mission called the Euclid Space Telescope. This telescope was made to study two of the biggest mysteries in modern science: dark energy and dark matter. These invisible forces make up most of the universe, but we still know very little about what they really are. Dark energy, especially, is thought to be why the universe is not just expanding, but expanding faster and faster over time. Scientists built Euclid to help map out the shape and structure of the universe by looking at where galaxies and galaxy clusters are and how they move over time. By making a kind of cosmic map, they hope to see how dark energy has affected the universe's growth and what it might do in the future. This map could help answer some of the biggest questions in astronomy, like what dark energy really is, where it comes from, and how it changes the way space stretches and moves. Another exciting project to explore the universe's growth is the Square Kilometre Array, often called SKA. This is an international project to build the largest radio telescope on Earth. Unlike telescopes that use visible light, radio telescopes pick up radio waves which can travel through cosmic dust and gas more easily. This means SKA will be able to see parts of the universe that other telescopes cannot. SKA will have a huge network of antennas spread across large parts of the world, working together like one giant telescope. It will collect very detailed information about faraway galaxies, the afterglow of the Big Bang, and the overall structure of the universe. This will help scientists understand how galaxies formed, how matter and energy are spread across space, and how the universe's growth has changed the way everything is arranged on the larger scales. But watching galaxies isn't the only way to study cosmic growth. The next generation of gravitational wave detectors also has great promise. Gravitational waves are tiny ripples in the fabric of space and time, made when huge cosmic objects like black holes crash into each other. These ripples move across the universe and carry important information about how space itself behaves. A future mission called the Laser Interferometer Space Antenna, or LISA, will be able to detect gravitational waves much better than the tools we have now. By studying these waves, scientists will learn more about how space has expanded, both across the whole universe and on smaller scales. One of the best things about gravitational waves is that they are not blocked by matter or light, which means they can travel freely across space and bring information that would otherwise be hidden. As our telescopes and detectors grow ever more powerful, the amount of information they collect becomes mind-boggling. We're no longer just looking at a few stars or galaxies, we're gathering billions and billions of pieces of data. Handling such enormous amounts of information would be impossible without the help of artificial intelligence and machine learning. These clever computer programs are becoming indispensable in modern astronomy. Scientists now rely on AI to spot hidden patterns, pick out important signals, and even make predictions about how galaxies behave and change over billions of years. AI is especially valuable when studying the expansion of the universe. By tracking how galaxies drift apart and evolve over cosmic time, these tools help researchers test ideas about dark energy, the mysterious force that seems to be pushing the universe to expand faster and faster. They allow us to glimpse possible futures for the cosmos, far beyond what our eyes alone could ever see. Another critical piece of the puzzle comes from the cosmic microwave background, or CMB, which is the faint leftover radiation from the Big Bang itself. This ancient glow holds clues to the universe's earliest moments. Space telescopes like Planck, which launched in the year 2009, have already mapped the CMB in incredible detail. These maps reveal tiny fluctuations in temperature and energy that, over billions of years, led to the formation of galaxies, clusters, and the large-scale structures we observe today. But scientists are not stopping there. They are planning even more advanced missions to study the CMB more closely. These future explorations may help unlock the secrets of cosmic inflation, a brief period when the universe expanded unimaginably fast, just moments after the Big Bang. On our own planet, the Vera Rubin Observatory, a groundbreaking new telescope under construction in Chile, promises to revolutionize the way we study the universe's expansion. By continuously scanning vast swaths of the sky, it will capture deep and wide images, following the motion of millions of galaxies and recording how their positions shift over time. This massive endeavor will provide an unprecedented look at how dark energy influences the motion of galaxies and even supernova, those spectacular explosions of dying stars. Because the Rubin Observatory will repeatedly observe the same areas of the sky, it will also be ideally suited for catching rare or unexpected cosmic events as they happen. This could allow scientists to witness phenomena related to cosmic expansion in real time, offering clues that were once completely out of reach. Yet despite all these advances, one profound question remains. Can we ever fully grasp the true nature of cosmic expansion? The idea that the universe is stretching outward, perhaps endlessly, is one of the most mysterious and awe-inspiring concepts in all of science. Even with our remarkable discoveries about galaxies drifting apart and the methods we use to measure the growth of space, there remain enormous unknowns. For instance, while we know that dark energy is driving the acceleration of the universe's expansion, we still have no real idea what it is. Is it some kind of force, a strange new field, or simply a property of space itself? Even more puzzling, why did dark energy begin to dominate the universe at a specific moment in cosmic history? These are questions that go to the very core of what the universe is and how it works. There is also the enigma of the cosmological horizon, a boundary beyond which we can never see or receive information. It is as if we are living inside a vast cosmic bubble, while the rest of the universe lies forever hidden. Will we ever know what lies beyond this horizon, or are those regions destined to remain eternally out of reach? Even within the regions we can observe, the complexity of cosmic expansion is staggering. Physicists use extremely sophisticated mathematics and computer models to describe how space stretches, how galaxies form, and how dark energy might behave. Yet describing something is not the same as fully understanding it. We can predict the movement of galaxies with incredible precision, but the deeper why behind it all remains elusive. Part of the challenge comes from the limits of our own minds. Our brains evolved on a small, stable planet, where time flows steadily, space feels fixed, and forces behave in familiar ways. The universe, on its grandest scales, often ignores these everyday rules. Time may flow differently in distant corners of space, and the idea of infinite space, endlessly stretching with no edge, goes far beyond what our minds are naturally equipped to imagine. Some thinkers suggest that there may always be parts of the universe beyond human comprehension, not because we lack clever tools or advanced equations, but because the cosmos may be so astonishingly complex that the human brain cannot fully grasp it. Still, the human spirit has always reached for the impossible. There was a time when the very idea of an expanding universe seemed like science fiction. Today, it stands as a central truth of modern cosmology, and while some mysteries may never be fully solved, others may one day be unlocked by the next powerful telescope, the next brilliant theory, or the next curious mind ready to explore the heavens. For thousands of years, people believed that Earth was at the very centre of everything in the universe. To them, this idea seemed perfectly natural. Every day they would look up at the sky and see the sun rise in the morning, climb high above, and then sink slowly in the evening. They watched clouds drifting gently across the blue, saw the moon glow softly at night, and noticed countless stars scattered like tiny glittering jewels across the deep darkness. Everything in the sky appeared to move around them, while Earth itself seemed steady, solid, and unmoving. So they concluded that all the stars, all the planets, and every point of light in the night sky must be circling around their home, our Earth. This way of thinking was not limited to one place or one people. Ancient civilizations from China to the Maya in the Americas shared similar ideas about the heavens. Yet it was in the Greek-speaking world, often called the Hellenic world, that this belief became more than just a story. There, it was transformed into a detailed, logical system that tried to explain the movements of the skies with careful reasoning. The person most responsible for turning this old belief into a full-fledged model of the universe was a scholar named Claudius Ptolemy. Ptolemy lived in Alexandria, Egypt, during the 2nd century of the Common Era, a time when Egypt was ruled by the Romans. He was not just an astronomer, he was also a mathematician, a philosopher, and a thinker who wanted to describe the heavens with precision. He inherited centuries of knowledge, star charts from Babylon, careful observations of the skies from Egypt, and Greek ideas about geometry. But what he did with this information was extraordinary. He organized it, refined it, and shaped it into a grand system, which he wrote down in a massive book later called the Almagest. This book was so powerful that for more than 1,000 years it became the ultimate guide to understanding the universe. In Ptolemy's model, Earth sat still at the very centre. Around it, in perfect layers, moved the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and then the distant sphere of stars. Beyond this outermost layer, he said, lay nothing that humans could see or know. Ptolemy imagined the universe as a series of clear, crystal-like spheres, each carrying a celestial body, all turning smoothly around Earth. The stars were fixed to the outermost sphere, which spun once every day, creating night and day for everyone below. This was not just a guess. Ptolemy used numbers, careful measurements, and records of past observations to make his system work mathematically. Like many Greek thinkers before him, he believed that the circle was the most perfect shape, so the heavens had to move in perfect circles. But a problem soon appeared. When people watched the planets, especially Mars, Jupiter, and Saturn, they noticed something strange. At times, a planet would seem to slow down, stop, and even move backward for a while before continuing forward again. This strange behaviour, called retrograde motion, did not fit neatly into the idea of simple circles around Earth. To solve this puzzle, Ptolemy introduced the concept of epicycles. An epicycle was a small circle that a planet travelled along, while that small circle itself moved around Earth on a larger circle called the deferent. In other words, the planet circled a point that itself was circling Earth. This looping motion could explain the backward steps observed in the night sky. Yet even this adjustment was not enough to perfectly match reality. Ptolemy then added another idea, the equant, an imaginary point slightly offset from the true centre of Earth. From this shifted perspective, the motion of planets appeared smoother and more regular. Over the centuries, Ptolemy's model grew increasingly detailed. Scholars copied it, refined it, and used it. It shaped calendars, guided sailors across oceans, supported astrology, and influenced religious thought. For more than 1,000 years, this geocentric system was accepted as truth, but cracks began to appear. Observers started asking whether there might be a simpler, more elegant explanation for the movements of the heavens. Then, in the year 1543, a quiet revolution began. A book was published that would shake the very foundations of astronomy. Its Latin title was De Revolutionibus Orbium Celestium, which means On the Revolutions of the Heavenly Spheres. The author was not a famous king or philosopher, but a church priest named Nicholas Copernicus. That may sound unusual today, but at that time, the church was the centre of learning across Europe. If someone wanted to study mathematics, astronomy, medicine, or philosophy, they usually did so through the church. Monasteries and cathedral schools served as libraries, laboratories, and centres of research. Copernicus, born in what is now Poland, studied law, medicine, and even economics. He learned Greek and Latin fluently. But above all, his lifelong passion was the sky, the stars, the planets, and the mysteries of the universe. For many years, Copernicus watched the sky, did calculations, and quietly developed an idea that went against everything he'd been taught. He believed the sun, not the Earth, was at the centre of the universe. Earth, he said, was just another planet like Mars or Jupiter, and it went around the sun once every year. That was not all. Copernicus suggested that Earth itself moved in 3 different ways. The first was spinning. He said that Earth turns on its axis once every 24 hours. That spin explains why the stars rise and set every night. The second was orbiting. He said Earth goes around the sun once a year, and that is why the planets change positions and the seasons change. The third was a slow wobble in Earth's tilt, a circular movement that we now call precession. Copernicus did not just guess these things. He spent many years making detailed geometric models and using trigonometry to figure out the distances of the planets from the sun. He noticed that the closer a planet was to the sun, the faster it seemed to move across the sky. That matched perfectly with his model. Still, Copernicus thought planets moved in perfect circles, just like Ptolemy. Because of this, his predictions were not much better than the old system. Sometimes, they were even less accurate. But the real discovery was still ahead. Not long after, a new tool appeared in Europe, the telescope. It was not made by a scientist, but by Dutch lens makers who put pieces of glass together for curious buyers. News of this tool spread quickly, and when it reached Italy, one man saw that it could change everything. Galileo Galilei did not invent the telescope, but he turned it into something much more powerful than a tool for sailors or soldiers. He made it into a scientific window to the sky. In the year 1609, he pointed his handmade telescope toward the night sky, and what he saw shook the foundations of old ideas forever. The first thing Galileo looked at was the moon. For thousands of years, people believed the moon was a flawless divine sphere, a perfect and shining lamp in the sky. But when Galileo looked through the glass, he saw something no one had really seen before. The moon was not perfect. It had craters dug into its surface, mountains that cast long shadows, and valleys that were rough like the lands on Earth. The moon suddenly looked less like a sacred jewel, and more like a real world. It was scarred, shaped, and rough, just like our own planet. Then Galileo turned his telescope to Jupiter, the biggest planet in the solar system. He saw 4 tiny points of light moving around it. At first, he thought they were stars, but night after night as he watched, these little lights changed positions. They moved around Jupiter, staying close, never drifting far. Galileo realized these were moons, 4 moons orbiting Jupiter. This discovery was huge, because according to the old model, everything in the sky was supposed to move around Earth alone. Yet here was Jupiter, holding its own small system of worlds. Earth was no longer the center of all movement. Galileo did not stop there. He looked at Venus, the bright planet that shines like a star in the evening. What he saw became the final proof. Venus had phases, just like the moon. Sometimes it looked full, sometimes thin like a crescent, and sometimes half-lit. This could only happen if Venus went around the Sun. If Venus had orbited Earth as the old model said, it would never have shown these changing shapes. But if Venus went around the Sun, and Earth moved too, then everything made sense. That small shining planet showed the truth. Copernicus had been right all along. But even though Galileo showed the vision, he did not solve the math. That job went to Johannes Kepler, a German mathematician and skywatcher who was both deeply religious and very precise. Kepler's life changed when he became assistant to Tycho Brahe, the last great astronomer who had studied the sky without a telescope. Tycho Brahe was a Danish nobleman obsessed with accuracy. For decades, he built huge measuring tools on his private island observatory. Without a telescope, he recorded the positions of planets with amazing care, writing down their movements every night. Still, Tycho did not fully believe the Copernican model. Instead, he made his own mixed theory. He thought the planets went around the Sun, but the Sun went around Earth. It was an attempt to balance old ideas with new ones. When Tycho passed away in the year 1601, his large collection of planetary data went to Kepler. Kepler worked hard, determined to see if the Copernican system really matched Tycho's careful records. He focused especially on Mars, but Mars was tricky. It did not move smoothly across the sky. Sometimes it sped up, sometimes slowed down, sometimes went backward in strange loops. For years, Kepler tried to force Mars into neat circular paths, because circles were thought to be perfect and holy. But no matter how hard he tried, the numbers did not match. Finally, Kepler gave up his old ideas. He let the data speak. And when he did, the sky showed its secret. Mars, and all the planets, did not move in perfect circles. They moved in stretched circles, ellipses. This became Kepler's first law of planetary motion. All planets move in elliptical orbits with the Sun at one focus of the ellipse. But Kepler did not stop there. He saw another pattern. As planets moved around the Sun, they did not go at the same speed. They moved faster when closer to the Sun and slower when farther away. This became Kepler's second law. A line drawn between a planet and the Sun sweeps out equal areas in equal times. No matter how close or far a planet is, the area it covers in the same amount of time is always the same. This explained Mars's strange movements and brought order to the sky. Finally, Kepler discovered the third law, the law of periods. He found that the time a planet takes to go around the Sun is connected to its distance from the Sun. In simple words, the farther a planet is from the Sun, the longer its year will be. The pattern was exact and mathematical, a universal rhythm of movement in space. With Galileo's telescope and Kepler's math, humans gained both vision and proof. Copernicus had sparked the idea. Galileo added fuel. Kepler built the rules that let the fire keep burning. And yet, after these discoveries, one big question remained. Why did the planets move at all? What force kept them circling instead of flying off or crashing into the Sun? The answer came from Isaac Newton and the story of the falling apple. Newton named the invisible force gravity. He realized that the same pull that made an apple fall to the ground also held the moon in its orbit, kept Earth near the Sun, and controlled the great dance of the planets. He made the law of universal gravitation. Every object with mass pulls on every other object, and the strength of the pull depends on how big the objects are and how far apart they are. With this remarkable law, Isaac Newton connected the heavens and the earth in a single grand system. The same principles that explained why an apple falls from a tree also describe the movements of distant stars. Using Newton's equations, astronomers could now figure out exactly how fast Earth travels around the Sun, about 107,000 kilometers every hour, which is almost 30 kilometers every single second. Mercury, being much closer to the Sun, races along even faster, reaching nearly 47 kilometers every second, while Mars, lying farther away, drifts more slowly in its orbit. The pattern was clear and elegant. The nearer a planet is to the Sun, the faster it must travel to stay in its path. Newton's work wove the final thread into the grand tapestry of cosmic understanding. For the very first time in human history, there was a single set of laws that applied everywhere, whether it was a falling stone on Earth or the sweeping motion of stars and planets across the sky. Yet even as this great understanding spread, a deeper and more thrilling mystery began to emerge. As astronomers sharpened their telescopes and refined their calculations, they discovered something truly astonishing. The Sun itself, which for centuries had seemed like the fixed anchor of the heavens, was not standing still at all. It too was moving, carried along on an even larger journey through the vast cosmos. After the Great Copernican Revolution, the way humans saw the world changed forever. For thousands of years, people had believed that the Earth was the fixed centre of everything, the unmoving heart of creation. But Copernicus had dared to suggest otherwise. The Sun, not the Earth, sat at the centre, while our planet spun on its own axis and journeyed around the Sun once every year. This was not just a small shift in thinking, it was a complete upheaval of the way humans understood the cosmos. At first, many found the idea shocking, even dangerous. Yet, as the new heliocentric model gradually gained acceptance, it began to settle firmly into people's minds. The Sun, which had once been considered merely another shining light in the heavens, now became something far grander. It was no longer just a star among stars, it was the solid, steady anchor of the universe, the great lamp at the centre of everything. For a few centuries this image of the Sun held unchallenged, but change was coming again. This time, the challenge would not arrive from a philosopher or a mathematician, but from a man whose first love was music. William Herschel was born in Germany in the year 1738. As a young man, he moved to England, not to study the heavens, but to pursue a career as a composer. Yet alongside his music, he developed an extraordinary fascination: telescopes. In his spare time, he taught himself how to grind mirrors and polish lenses. His designs became so precise and innovative that they often outshone the best instruments of his era. When Herschel pointed his telescopes toward the night sky, he did more than look. He measured, counted, and searched for patterns. He wanted to understand whether the countless stars were scattered at random or followed some hidden order. With the help of his sister, Caroline Herschel, he undertook a vast project, a careful survey of the heavens. Night after night they recorded the number of stars in narrow slices of the sky, slowly building a detailed record. Gradually a picture began to emerge. Herschel noticed that some regions of the sky were far more crowded with stars, especially along a faint glowing band, the Milky Way. From these observations he constructed a map. The stars were not infinite in every direction, he realized. Instead, they formed a massive flattened system, like a giant wheel or disk. And at the centre of this system he placed the Sun. Today, we know that Herschel had underestimated the universe's true scale. Interstellar dust hid many distant stars from view, making the galaxy seem smaller than it really was. But for the late 18th century his insight was astonishing. He had shown that the stars were not infinite and aimless. They belonged to a structured system, one that included the Sun and Earth. He called it the galactic system. Herschel did not realize that some of the hazy patches of light he observed, the so-called nebulae, were actually entire galaxies, unimaginably far away. Even so, his work was revolutionary. He had demonstrated that humans were not at the center of everything. Not even close. His flat map of the stars carried a hidden message. If the Milky Way had a shape, it must also have direction and motion. If the stars formed a structured system, then the Sun, and the Earth with it, had a specific location. And if it had a location, perhaps it was moving through space as well. This question, are we in motion, and how could we know, puzzled astronomers. There was a deeper problem too. Every observation we make comes from Earth. Our eyes, telescopes and instruments all rest on this restless planet, which spins on its axis and orbits the Sun. And perhaps the Sun itself is moving through space. How then can anyone determine what is truly still and what is moving? This is where the concept of a frame of reference becomes important. Imagine a simple scenario. You're sitting in a train. Inside the carriage, everything seems calm. A cup of coffee sits steadily in your hand. A book rests quietly on your lap. Outside the window, you see another train beside you. For a moment, it appears as though that train is sliding backward. But then you wonder, is it your train that is moving, the other train, or are both in motion? Without seeing the ground, you cannot be certain. From inside your train, the world feels still. Yet to someone standing on the platform, you're rushing past at 80 kilometers an hour. Both views are correct. Motion is not absolute. It is always relative. The universe works in the same way. From our moving Earth, circling a moving Sun, it becomes a complex puzzle to figure out what is really moving. One man quietly took on this challenge, Jacobus Kapteyn. He was not loud or dramatic, but a patient, careful thinker who loved numbers more than attention. Born in the Netherlands in the mid-19th century, he worked more than 100 years after Herschel had created his maps. By then, most scientists agreed that the Sun was inside a star system, the Milky Way, but the system's true shape and motion remained a mystery. Kapteyn began not with sweeping theories, but with meticulous data collection. He studied not only the brightness and positions of stars, but also their proper motion, tiny shifts in position over years or decades. These changes were often no more than fractions of an arcsecond per year, yet with careful calculation, they revealed a story. He gathered observations from across the globe, from observatories in South Africa, Argentina, Australia, and beyond. Piece by piece, he built enormous catalogues containing the positions, motions, and brightness of thousands of stars. Then a remarkable pattern appeared. The stars were not drifting randomly. They seemed to form two vast streams, flowing across the heavens like cosmic currents. At first glance, it appeared that the stars themselves moved in two large groups, each spinning in its own direction. But Kapteyn saw it differently. He realized that this apparent motion might not be the stars moving at all, but our own motion as observers. Like a person walking through a crowded plaza, the people around you seem to drift in different directions, but in truth, it is you who are moving. Kapteyn carefully applied his calculations, and the results were remarkable. They fit together perfectly. The way the stars moved across the sky only made sense if the Sun itself was not standing still, but drifting through space, carrying the Earth and all its planets along with it. Astronomers later called this direction of the Sun's motion the solar apex. According to Kapteyn's findings, the Sun was steadily travelling toward a point in the constellation Hercules at roughly 20 kilometers per second. It was not a fiery, racing sprint, but a calm, persistent glide through the galaxy. With this realization, the Sun lost its long-held image of being still and fixed in space. But Kapteyn was not satisfied with just that. If the Sun was moving, then what was the larger system it was moving inside? What shape did our Milky Way galaxy have? Using his observations of how stars moved and how bright they appeared, Kapteyn tried to build a picture of the galaxy as a whole. He assumed that stars were spread evenly across space, and that they became fainter as they got farther away. From this, he imagined the Milky Way as a large, flattened disk, about 40,000 light-years across, with the Sun sitting close to its centre. This was humanity's first real attempt to map the entire Milky Way. Today, we know Kapteyn's map was too small, because he did not yet know about dark clouds of interstellar dust that block the light of distant stars. These clouds made the galaxy appear smaller and simpler than it actually is. Still, for his time, Kapteyn's work was astonishing. He had taken the scattered motions of stars and turned them into a coherent cosmic map. Then came a moment that would forever change astronomy. For centuries, people had noticed faint misty patches in the night sky, scattered among the stars. These were called spiral nebulae. At first, most astronomers assumed they were just clouds of gas or small star clusters within our Milky Way. But some began to wonder, could these misty patches be much bigger? Could they be entirely separate star systems, islands of stars far beyond our own galaxy? This question set the stage for one of the greatest discoveries in science. Edwin Hubble was the astronomer who would change everything. In the early 20th century, he worked with the Hooker telescope on Mount Wilson in California. At that time, it was the largest and most powerful telescope in the world, with a mirror more than 2.5 meters across. It could see farther into the universe than anything that had come before. In the year 1923, Hubble pointed this enormous telescope at the Andromeda Nebula, one of the brightest of the mysterious patches in the sky. What he found inside would forever change humanity's understanding of the cosmos. Hidden among Andromeda's countless stars, Hubble discovered a special kind of star called a Cepheid variable. Unlike most stars, Cepheids do not shine steadily. They pulse, growing brighter and dimmer in a repeating cycle. The length of this cycle is directly related to the star's true brightness. Years earlier, Henrietta Swan Leavitt, a brilliant astronomer at Harvard College Observatory, had discovered the exact relationship between a Cepheid's pulsing period and its luminosity. This meant that astronomers could use Cepheid stars as cosmic measuring sticks. By comparing how bright a Cepheid appeared from Earth to how bright it truly was, they could calculate its distance. Hubble made that calculation, and the result shocked him. The Cepheid star in Andromeda was so faint that it had to be millions of light years away, far beyond the edge of the Milky Way. This proved that Andromeda was not just a small cloud within our galaxy. It was a galaxy of its own, an immense star system containing billions of stars. This was a revolutionary discovery. For all of human history, people had thought the Milky Way was the entire universe. Now, it became clear that our galaxy was just one of countless others, a single island drifting in a vast cosmic ocean. With this discovery came a new perspective. Because we live inside the Milky Way, we cannot step outside it to see its shape directly. It is like standing at the base of one tree and trying to describe an entire forest. But by studying other galaxies, astronomers now had something to compare against. They could ask questions. Does the Milky Way have spiral arms like Andromeda? Does it have a dense central bulge, a surrounding halo, a flat rotating disk? By comparing our galaxy to others, astronomers began piecing together its structure. Over the decades that followed, progress was steady. Scientists mapped clouds of gas, star clusters, and various types of stellar populations. They developed new ways to observe the galaxy, including radio astronomy, which could see through the thick curtains of dust that block visible light. Slowly, a more detailed and accurate picture of the Milky Way began to emerge. Among the astronomers working on this puzzle was a Dutch scientist named Jan Oort. He studied the motions of stars in the Sun's neighbourhood. He noticed something curious. Stars did not move as they would if the Milky Way were a solid wheel. In a solid wheel, like the spokes of a bicycle, every part turns at the same speed. But stars did not behave this way. Some lagged behind, while others moved ahead. Oort realised that the galaxy rotated more like a whirlpool, with the inner regions moving faster than the outer ones. By carefully crunching the numbers, the Dutch astronomer Jan Oort discovered two important values, today known as the Oort constants, that describe how stars near the Sun move. Using these constants, he estimated that our Sun sits roughly 30,000 light-years away from the very centre of the Milky Way galaxy. But that was not all. Oort also calculated that the Sun is hurtling through space around the galactic centre at more than 200 kilometres every single second. To give a sense of that incredible speed, the Sun could travel around the entire Earth 7 times in just 1 minute. At this astonishing pace, it takes the Sun about 225 million years to complete one full orbit of the Milky Way. Astronomers call this immense period a galactic year, and every star twinkling in the night sky is on the same journey, circling the hidden centre of our galaxy, like countless dancers following an invisible rhythm. But what could possibly sit at the galactic centre, holding this enormous system together? Ordinary telescopes could not see it. To probe this mystery, astronomers turned to radio waves, focusing on the faint 21 centimetre signal naturally emitted by neutral hydrogen atoms. This signal could slip through thick clouds of cosmic dust that block normal light, allowing scientists to map the spiral arms of the Milky Way from the inside. The next giant leap came with the creation of the Very Long Baseline Array, or VLBA. Instead of a single telescope, the VLBA is a network of 10 enormous radio antennas, spread out across thousands of kilometers, from Hawaii in the Pacific Ocean all the way to the Virgin Islands in the Atlantic. By connecting them with incredible precision, astronomers effectively built a telescope the size of a continent. With it, they could measure movements so tiny they were fractions of a millionth of a degree, small enough to detect a coin lying on the moon from here on Earth. Using the VLBA, astronomers tracked cosmic beacons called masers, powerful bursts of radio light emitted by clouds of gas around newborn stars. Masers are bright, compact, and fixed to specific regions in the galaxy, making them perfect markers. By observing these masses year after year, astronomers measured both their positions and their motions with extraordinary precision. They combined proper motion, the slow drift of objects across the sky, with radial velocity, the change in wavelength that shows whether an object is moving toward or away from us. Together, these measurements allowed scientists to construct a full, three-dimensional map of stellar motion. The picture that emerged revealed the grand dance of the Milky Way. Stars swirl around the galactic center, not in neat circles but along winding spiral patterns shaped by gravity. Some spiral arms stretch forward, while others lag behind. Gas clouds twist and shear under tidal forces, star clusters wobble along their paths, and at the heart of this cosmic choreography lies something extraordinary. Near the galactic center, objects are racing at terrifying speeds, far faster than the visible stars, gas and dust could account for. Simply put, there was not enough ordinary matter to create the gravity needed. Something invisible was holding the galaxy together. All calculations pointed to a compact, dense, radio-bright point near the constellation Sagittarius. This mysterious object became known as Sagittarius A star, or Sagittarius A. As radio telescopes focused in closer, the evidence became undeniable. At the very center sits an object with a mass more than 4 million times that of our Sun, confined in a space smaller than the orbit of Mercury. No known material could be that dense. The only explanation that fits is a black hole. Today, Sagittarius A is recognized as a supermassive black hole, the anchor of our galaxy. It sits there quietly, mostly unseen, while stars, planets, and clouds of gas swirl endlessly around it. Even this, however, is not the end of the story. The Milky Way is far from static. It twists, warps, and wobbles as it spins. The spiral arm we call the Orion Spur, home to our solar system, rises and falls gently above the galactic plane, as if riding an invisible wave. Beyond that, the Milky Way itself drifts through the cosmos, tugged by unseen forces, part of an even larger cosmic dance stretching across intergalactic space. When a star, or even a whole galaxy, moves toward us, something interesting happens to its light. The light waves get squeezed, and the colour of the light shifts slightly toward blue. Scientists call this a blue shift. On the other hand, if the star or galaxy is moving away, its light waves stretch out, shifting toward red. This is called a red shift. It is a simple idea, but it holds the key to understanding the movement of the universe. In the years of 1910 and 1920, astronomers began using this clever technique to measure how stars and galaxies move. Among them was a man who would change our understanding of the universe forever, Edwin Hubble. His discoveries were nothing short of astonishing. When Hubble studied distant galaxies, he found that most of them were not sitting still in space. They were flying away from us. Even more surprising, the farther a galaxy was, the faster it was moving. Some galaxies were speeding off at hundreds of kilometers per second, while others were racing at thousands. Every observation confirmed the same pattern. The farther away, the faster the galaxy was fleeing. The only explanation was that space itself was expanding. Galaxies were not moving through space on their own. They were being carried along as space stretched. This was one of the greatest breakthroughs in the history of science. It revealed that the universe had a beginning, that everything we see today was once packed tightly together. It also laid the foundation for what would later become the Big Bang theory. But not every galaxy was moving away. One in particular stood out, a large spiral-shaped neighbour we now know as the Andromeda Galaxy. In the year 1912, an American astronomer named Vesto Melvin Slipher pointed his telescope at Andromeda and studied its light. At that time, the ideas of redshift and blueshift were still new. What Slipher discovered shocked the world. Andromeda's light was blue-shifted. Unlike almost every other galaxy, it was moving toward us, not away. Back then, astronomers could only say that Andromeda was coming closer. They didn't yet have the tools to understand the full story. 100 years later, however, the picture became much clearer. Today, astronomers use powerful space telescopes, giant supercomputers, and networks of radio antennas spread across Earth. By combining data from NASA's Hubble Space Telescope, the Gaia mission, and the Very Long Baseline Array of radio antennas, scientists tracked Andromeda's motion in 3 dimensions over many years. The result was clear: Andromeda is not drifting gently nearby. It is on a direct collision course with our Milky Way galaxy, and our galaxy is heading toward it as well. Right now, Andromeda is rushing toward us at about 110 kilometers per second, which is more than 400,000 kilometers every hour. But the Milky Way is moving too. Including the motion of our local group of galaxies, our galaxy is drifting toward Andromeda at nearly 300 kilometers per second. Altogether, the distance between us and Andromeda is closing at a staggering speed of about 500 kilometers per second. Even so, space is unimaginably vast. Andromeda is roughly 2.5 million light-years away. That equals about 24 quintillion kilometers, a number so enormous it is almost impossible to picture. This means that, even though the galaxies are hurtling toward each other, the collision is not imminent. It will not happen tomorrow, next year, or even in the next million years. The actual encounter is expected in about 4 to 5 billion years. Many people imagine a galactic collision as a fiery smash, stars crashing into one another, chaos everywhere. But that is not how it will happen. Despite their glowing appearance, galaxies are mostly empty space. Stars are very far apart. In our part of the Milky Way, the average distance between 2 stars is about 4 to 5 light-years, nearly 40 trillion kilometers. Even in dense regions, stars are separated by at least 1 light-year. To imagine it differently, if a star were the size of a ping-pong ball, the nearest star would be hundreds of kilometers away. This means that when the Milky Way and Andromeda meet, most stars will pass each other without colliding, drifting like ships silently gliding past one another. Some stars in crowded central regions might collide, and others at the edges could be flung out into deep space. The dramatic changes will come not from stars smashing together, but from gravity. This invisible force will stretch, twist, and reshape both galaxies. Long, thin streams of stars, tidal tails, will be pulled out like cosmic ribbons. Spiral arms will be torn apart, and the dense cores will move closer together until the 2 galaxies merge into a single massive system. The merger will not happen instantly. The first encounter will be a close pass, stirring up chaos. But the complete merging, a slow gravitational dance, will take about 1 to 2 billion years. It will not be a violent crash, but a long, graceful cosmic ballet. When the dance is complete, a new galaxy will be born. The Milky Way and Andromeda will form a giant elliptical galaxy astronomers call Milkomeda. It will not have the neat spiral arms we see today. Instead, it will be rounder, puffier, and brighter, a glowing sphere of stars, gas, and dust. Our Sun, if it still exists, will likely take a new orbit, far different from the one it has now, drifting unpredictably through this reshaped galaxy. And this story of Andromeda and the Milky Way is only one chapter. Our galaxy, along with Andromeda and hundreds of nearby galaxies, is moving towards something even greater. To see the full journey, we must look far beyond the solar system, past the Milky Way, and beyond our local group of galaxies. Galaxies are not scattered randomly. They gather in clusters drawn together by gravity, moving across the cosmos like rivers flowing toward a larger ocean. Our Milky Way is not wandering through the universe alone. It belongs to a small family of galaxies known as the local group. This neighbourhood is home to roughly 80 galaxies, some big, some small, scattered across a space nearly 10 million light-years wide. Within this cosmic family, two giants tower above the rest, our own Milky Way and the enormous Andromeda galaxy. Each of these massive galaxies is surrounded by smaller companions, called satellite galaxies, which orbit around them much like moons circle a planet. In the case of the Milky Way, these include the large and small Magellanic Clouds, bright patches of stars visible from the southern hemisphere. Around Andromeda, tiny galaxies like Messier 32 and Messier 110 whirl gracefully, as if dancing in loyalty to their giant host. But the local group is just one small corner in a much vaster cosmic city. Step up a level, and you find galaxy clusters, immense gatherings of galaxies, bound together by the invisible hand of gravity. Our local group is but a modest member of the Virgo cluster, a collection of more than 1,000 galaxies stretching across the sky. The Virgo cluster sits about 65 million light-years from us, and its gravitational pull is constantly tugging at our cosmic neighbourhood. The Milky Way and all the galaxies in the local group are not floating aimlessly. They are racing toward the centre of Virgo at a staggering speed of roughly 600 kilometres every second. Even galaxy clusters are only one layer of the universe's grand design. Clusters themselves can assemble into enormous superclusters, the titanic giants of the observable cosmos. These structures can span hundreds of millions of light-years and cradle tens of thousands of galaxies within their sprawling reaches. Our home supercluster is called Laniakea, a Hawaiian word meaning immense heaven. The name is perfectly fitting. Laniakea stretches across more than 500 million light-years and contains nearly 100,000 galaxies. Within its vast expanse lie famous clusters such as Virgo, Hydra Centaurus, Pavo Indus, and the Southern Supercluster, all woven together by an intricate cosmic web of galactic flows. But how do astronomers know all of this? How can they measure where galaxies are, how fast they move, and the directions in which they travel? The secret lies in tracking motion. Over the past several decades, astronomers have not only mapped the positions of galaxies, but also traced how they drift through space. To do this, they needed more than the usual redshifts and blueshifts, which reveal whether galaxies move toward or away from us. They had to measure a more subtle kind of motion, peculiar velocity, the speed at which galaxies move relative to the general expansion of the universe. Measuring this sideways drift is no easy task. You cannot simply snap a picture and read it off. Astronomers use clever tools, one of the most important being the Tully-Fisher relation. This method connects a spiral galaxy's brightness with how fast it spins. By comparing how bright a galaxy should appear to how bright it actually looks from Earth, scientists can estimate its distance. Once they know both distance and redshift, they can calculate whether a galaxy is moving faster or slower than the universe's expansion. The difference between these speeds reveals its peculiar velocity, motion caused not by cosmic expansion, but by local gravitational forces. These measurements form the backbone of the Cosmic Flows surveys. Cosmic Flows 2, and later the more detailed Cosmic Flows 3, collected enormous amounts of data, charting distances and motions of thousands of galaxies. They employed methods such as the Tully-Fisher relation, surface brightness fluctuations, and even type Ia supernovae as cosmic measuring sticks. With this treasure trove of information, astronomers built a three-dimensional velocity map of our cosmic neighbourhood, showing not only where galaxies are but also how they flow through space. The results were astonishing. Galaxies were not scattered randomly, like confetti blown by the wind. Instead, they streamed together in a coherent motion, flowing toward a mysterious region hidden behind the thick dust of our Milky Way, beyond the constellations Centaurus and Norma. This invisible source of gravitational pull became known as the Great Attractor. The first hints of the Great Attractor emerged in the 1970s, when astronomers noticed that galaxies, including our own, were sliding sideways through space at hundreds of kilometers per second, as if pulled by something enormous. Yet when telescopes pointed in that direction, they hit the so-called zone of avoidance, a dense, dusty region filled with stars and gas that obscured the view. Still, the motion could not be ignored. The gravitational tug was real, even if the object itself could not be seen directly. Over time, using X-ray observatories and infrared surveys capable of peering through the dust, astronomers slowly pieced together the puzzle. They discovered enormous masses of galaxies in that hidden region. One of the largest was the Norma cluster, lying roughly 220 million light-years away. But Norma was only part of a far greater structure, the Shapley Supercluster, one of the largest known superclusters near us. The immense gravity of the Shapley Supercluster bends the paths of galaxies across vast stretches of space, pulling our local group, the Virgo cluster, and even the entire Laniakea supercluster toward it. Yet the journey is not a simple straight fall into this cosmic giant. Space is far from uniform and gravity does not pull in a single straight line. Instead, we're caught in a cosmic tug-of-war. While the Great Attractor and the Shapley supercluster draw us one way, another force subtly shapes our motion in the opposite direction, the mysterious dipole repeller. The dipole repeller is not a galaxy or a cluster, it is a cosmic void, a vast empty region almost completely devoid of matter. And strangely, emptiness has power. While massive objects pull galaxies toward them, enormous voids act like open lanes, letting galaxies drift away more freely. Imagine floating down a river. On one side, a roaring waterfall pulls you forward. That is the Great Attractor. On the other side, the water is calm and flat. That is the dipole repeller. You're not being pushed by the void, but its absence of pull allows the stronger currents to guide you. In the end, the waterfall wins, and we drift inexorably toward it. In the year 2017, astronomers finally confirmed a remarkable picture of our cosmic neighbourhood, thanks to data from the Cosmic Flows 3 project. This project had carefully mapped the motions of more than 18,000 galaxies, charting their paths across space with extraordinary precision. What they found was astonishing. Galaxies are not merely drifting randomly. They are being tugged toward a massive unseen concentration of matter known as the Great Attractor, while simultaneously flowing away from a kind of cosmic push, a region scientists call the dipole repeller. Together these forces form a giant cosmic pattern, a dipole, shaping the movements of galaxies across the nearby universe in a subtle but undeniable dance. But the story does not stop there. If we zoom out even farther, beyond individual galaxies, beyond clusters and superclusters, past the intricate filaments and yawning voids that make up the cosmic web, an even grander motion comes into view. The very threads of this enormous cosmic web are not fixed. They too are drifting, sliding and flowing across the vast reaches of the observable universe, all being drawn toward a mysterious destination that remains hidden from our sight. At the same time, something truly breathtaking is unfolding on the larger scales. Galaxies that are far, far away from us are not merely distant. They are moving away faster and faster, but they are not rocketing through space like tiny cosmic bullets. No, the truth is far more wondrous. The very fabric of space itself is stretching, and as space stretches, it carries these distant galaxies along with it, like leaves drifting on a slowly swelling river. Even more surprising, this great stretching of space is not slowing down. On the contrary, it is accelerating. Scientists call this the accelerating expansion of the universe. With each passing moment, galaxies recede from us more quickly. The farther a galaxy is, the faster it seems to flee. In the far future, some galaxies will move away so swiftly that, from our viewpoint, they will appear to exceed the speed of light. At first, this seems impossible, because we are often told that nothing can travel faster than light. Yet here is the remarkable twist. Those galaxies are not breaking any cosmic speed limits. They are not moving through space faster than light. Instead, it is the space between us and them that is expanding. This subtle but profound difference is perfectly consistent with the laws of physics. A simple analogy helps. Imagine raisins baked into rising bread dough. The raisins themselves are not racing through the dough, but as the dough swells, they are carried farther and farther apart. This expanding universe carries with it a sobering implication for the distant future. As space continues to stretch, the most remote galaxies will eventually drift so far away that even their light will never reach Earth again. They will not vanish in the literal sense, but their light will be lost to us, unable to cross the ever-growing distances. At that moment, they will pass beyond what scientists call the cosmic horizon, the ultimate boundary of our observable universe. This is not a distant fantasy. It is already happening. Even today, we observe galaxies so far away that the light reaching us began its journey billions of years ago. As time marches on, that light will be stretched ever more by the expanding universe. Scientists call this stretching redshift because it shifts the light toward the red end of the colour spectrum. The faster a galaxy recedes, the more its light is stretched and redshifted. Eventually, this light will be stretched so much that it will slip beyond the reach of our eyes and even the most powerful telescopes. It will first move into the microwave range, then into radio waves, and finally fade entirely from detection, disappearing into the silent darkness. If we imagine leaping forward billions of years into the future, most galaxies will have vanished beyond the cosmic horizon. Only those bound to us by gravity, our small cosmic family, will remain visible. This family, known as the local group, includes our Milky Way, the massive Andromeda galaxy, and a handful of smaller neighbouring galaxies. Because gravity holds them together, these galaxies will not drift apart. Instead, over unimaginable spans of time, they will slowly draw closer, eventually merging into one enormous galaxy. Beyond this small family, however, the rest of the universe, all other galaxies, stars and wonders, will quietly slip out of sight one by one into the vast, empty dark. This paints a picture of a universe that grows lonelier with time. Each distant galaxy that disappears takes its light, its history, and its role in the cosmic story with it. Future astronomers, trillions of years from now, may gaze at the night sky and see only one massive galaxy, the final union of the Milky Way and its companions. They might never know that a vast universe, once teeming with countless galaxies, once existed beyond their view. In the early universe, galaxies frequently collided and merged, igniting furious bursts of star formation and reshaping themselves dramatically. But as eons pass and galaxies drift ever farther apart, these fiery encounters will grow rare. The universe will become quieter, calmer, and profoundly more solitary. And in the far, far future, long after the last galaxy has slipped beyond sight, our own galaxy will change too. Stars will shine for billions of years, but eventually they will run out of fuel. New stars will no longer be born. One by one, the stars will fade, and the universe will grow colder and darker. This final state is called the heat death of the universe, a time when all energy is exhausted, when stars and galaxies no longer burn, and when the cosmos itself sinks into deep stillness. Throughout all this, the laws of physics remain unbroken. Gravity, thermodynamics, quantum mechanics, they continue to govern the universe, even as the stage on which they act expands and changes. Yet some scientists ask a daring question. Could the endless stretching of space eventually alter the very laws of nature themselves? Could constants like the speed of light, the strength of gravity, or the fine structure constant, which dictates how light interacts with matter, one day change? These constants are the foundation stones of reality. The speed of light is more than just a measure of how fast light travels. It sets the ultimate speed limit for all information in the universe. The gravitational constant governs how strongly objects pull on one another, from the Earth holding the Moon, to the Sun keeping the planets in orbit, to galaxies themselves holding together. Without it, there would be no stars, no planets, no galaxies, no universe as we know it. The universe we live in is grand, beautiful, and ever-changing, and its story, from the motions of galaxies to the very stretching of space itself, reminds us that the cosmos is alive with motion, wonder, and mystery, carrying us forward into a future both awe-inspiring and humbling. For the moment, all the evidence we have suggests that the fundamental constants of nature do not change. The universe is indeed growing larger, stretching outward in all directions, but the basic rules it follows seem to remain the same. Yet, the deeper we look into the far future, the more we find ourselves asking a tantalizing question. Is the very foundation of reality truly solid and unchanging? Or could there be some hidden surprise waiting to be revealed in the grand unfolding story of the cosmos? One particularly fascinating character in this cosmic tale is what scientists call the fine structure constant. This is a number that controls how light interacts with tiny charged particles, like electrons and protons. It is crucial for chemistry, for the way atoms bond together, and for the formation and behaviour of all matter. Even the tiniest shift in this number could completely reshape the universe. Imagine a reality where atoms could not form, where stars might never ignite, and where life as we know it could never exist. The story becomes even more captivating when we think about the expansion of the universe. This expansion is driven by a mysterious force called dark energy, which causes space itself to stretch, almost like an ever-inflating balloon. This cosmic stretching pushes galaxies farther apart and shapes the universe on a scale so vast that it is almost impossible to imagine. But a question arises: could this stretching of space also slowly influence the very rules that govern everything within it? Some scientists believe it might. They suggest that the constants we measure today, such as the strength of gravity or the force holding electrons to atoms, may not have always been exactly the same. Perhaps billions of years ago, the universe followed slightly different rules. If that were the case, the earliest universe could have looked very different, guiding the birth of the first stars and galaxies in ways we're only beginning to understand. The fine structure constant has especially captured the attention of researchers. A handful of studies hint that this number might have been just a tiny bit different billions of years ago. This idea remains uncertain and highly debated, but if it turns out to be true, it could mean that the universe's expansion, or possibly other unknown cosmic forces, can subtly shape the very laws of physics over time. Then there is the ever-enigmatic dark energy. Despite decades of research, we still do not fully understand what it is or how it behaves. Some theories suggest that dark energy could be linked to the evolving nature of the universe itself, and might even have the ability to gently influence these fundamental constants. The mysteries do not stop there. Some scientists have proposed that as the universe expands, our very experience of time could be affected. As space stretches, light waves become longer, and distances between objects grow ever wider. Could it be possible that time itself stretches along with space? Could the flow of time be changing in a profound and fundamental way? Even more extraordinary ideas have been imagined. Some researchers picture a universe that, over unimaginable billions or even trillions of years, might undergo dramatic transformations called phase transitions. Much like how water freezes into ice when it gets cold enough, the universe itself might shift into a completely new state. In this distant future, the laws of physics could reorganize, some rules might vanish, and entirely new ones could emerge. The universe that results could be utterly unrecognizable, far beyond anything we can picture or experience today. The ultimate fate of the universe has always been one of the most intriguing and profound questions that humankind can ask. Since ancient times, humans have gazed at the stars and wondered not only how the cosmos began, but also how it might one day conclude. Today, with the tools of modern astronomy and the frameworks of theoretical physics, scientists have developed a variety of visions for the universe's distant future. Each of these scenarios, however, pivots on one critical factor: the way the universe itself stretches and expands across the vast reaches of space. The expansion of the cosmos is not merely a simple outward motion, it is an ongoing dynamic process, an invisible force gently but inexorably pulling galaxies apart, stretching the fabric of space like an endlessly elastic sheet that grows ever wider with time. Understanding this expansion is key to imagining the fate of everything, from the tiniest atom to the largest galactic supercluster. The future of the universe depends on the delicate balance between the expansion of space and the forces acting within it. If the stretching continues endlessly, the cosmos may drift toward an ever more cold and empty state. If the expansion slows down or halts, gravity might eventually draw all matter back together. And in the rare theoretical twist where the expansion reverses completely, the universe could collapse under its own weight. These differing possibilities shape not only the movement of galaxies and stars, but also the behavior of fundamental forces and the flow of energy throughout the cosmos. The story of the universe's end is intimately linked to the story of its beginning, as every possibility stems from the same laws that have guided its evolution for billions of years. Among the earliest imagined scenarios is the one called the Big Crunch. In this vision, the universe does not expand forever. Instead, if there is enough mass and energy scattered across the cosmos, the force of gravity could ultimately overwhelm the expansion, halting it and then reversing it. The galaxies which now drift apart would gradually draw closer together once again. Stars would begin to fall inward, pulled toward one another, and planets, including the Earth, would slowly converge toward a common center. Over unimaginably long stretches of time, This contraction would continue until all matter and energy collapse into an extraordinarily dense point, a singularity that mirrors, in some sense, the Big Bang from which the universe originally emerged. It is as if the entire cosmic movie were being played in reverse, compressing eons of galactic motion, stellar evolution, and planetary drift into an infinitesimally small instant. Yet the Big Crunch, while dramatic and conceptually captivating, does not currently hold favour among most scientists. Observations over the past few decades have shown that the universe is not merely expanding, but accelerating in its expansion. The galaxies are moving apart faster and faster, and distant celestial objects recede from us more rapidly over time. This acceleration suggests that the idea of a cosmic collapse is unlikely, at least under current conditions. Still, scientists remain open to possibilities. If the mysterious force known as dark energy, which drives this acceleration, were to change its behaviour in the far future, the universe might yet find a way to slow its expansion, perhaps even reversing it under extraordinary circumstances. Beyond the Big Crunch, there exists a scenario that is even more subtle, strange, and rooted in the mysteries of quantum physics. This is the concept of vacuum decay, which imagines that the universe may not be in its most stable state at all. Instead, it could be lingering in a temporary delicate condition known as a false vacuum. While this state seems stable to us, quantum mechanics allows for the possibility that, purely by chance, a bubble of true vacuum could emerge spontaneously anywhere in space. Once formed, this bubble would expand at the speed of light, erasing everything in its path. Galaxies, stars, planets, and even atoms could vanish in an instant, replaced by a new state of space that is fundamentally different from our current universe. This process could occur without warning, and its timing would be entirely unpredictable. Unlike other scenarios which unfold over billions or trillions of years, vacuum decay could occur at any moment, leaving no opportunity to anticipate or avoid its consequences. The realm of theoretical possibilities extends even further when considering the idea of the multiverse, the notion that our universe might be just one of countless others. Some speculative models suggest that black holes could function as gateways to these other universes, providing conduits through which matter and energy might escape into new realms. In such visions, the death of our universe would not signify an absolute end, but part of a larger, ongoing cycle of birth and demise across an infinite array of cosmic regions. While our observable universe might fade, collapse, or transform, the multiverse itself could continue indefinitely, spawning new universes as old ones fade away. This perspective adds layers of complexity and wonder to the question of cosmic destiny, suggesting that the story of creation and destruction may extend far beyond the limits of our own space and time. Among all these possibilities, the scenario most widely considered likely is the slow, gradual fading of the cosmos into what is called the heat death, or big freeze. In this vision, the universe continues to expand forever. Galaxies drift apart, stars burn through their fuel and eventually extinguish, and the cosmos becomes increasingly cold and dark. The temperatures would fall to levels near absolute zero, leaving almost no energy available to sustain processes that require heat or light. Over unimaginable timescales, this expansion would create a universe that is vast, silent, and devoid of active sources of energy, a realm where almost nothing occurs and almost nothing survives. The implications of the Big Freeze are profound for life as we understand it. Life depends on energy flows, and in our current universe, stars are the ultimate suppliers of that energy. On Earth, sunlight drives nearly all biological activity, warming the planet and sustaining ecosystems. Without stars, or with stars long extinguished, these familiar energy sources would vanish, creating a universe that seems, at first glance, utterly inhospitable to living beings. Yet even in this extreme environment, scientists have speculated that life might find a way to endure. One of the most intriguing possibilities is that intelligent civilizations, if they exist and possess sufficient technological advancement, could harness alternative sources of energy. Black holes, which persist long after stars have expired, could serve as enormous reservoirs of power. When matter falls into a black hole, immense energy is released, and civilizations capable of capturing this energy could maintain structures, equipment, and even life itself long after ordinary stars have gone dark. In this scenario, life does not disappear merely because starlight fades. Instead, it adapts, finding ways to tap into more exotic and powerful cosmic resources. Life's potential to survive extreme conditions is already demonstrated on Earth through the existence of extremophiles, tiny organisms that flourish in environments previously thought to be uninhabitable. These creatures thrive in boiling hot springs, deep-sea hydrothermal vents, icy polar regions, and even radioactive zones. If life can persist in these extreme niches here, it is conceivable that, given sufficient time, it could evolve mechanisms to endure the frigid, energy-starved conditions of the far future. In a universe approaching the Big Freeze, life might operate according to entirely new chemical processes, requiring only minimal energy to continue its existence. Advanced civilizations might also develop technological solutions to survive the cold and darkness. They could build massive devices designed to collect, store, and recycle the remaining energy of the universe. Entire ecosystems might be enclosed within artificial habitats, maintaining warmth, light, and resources that the wider universe can no longer provide. Metabolic processes could be slowed, allowing life to stretch limited energy reserves over trillions of years. Time itself might become the most precious resource, with survival depending on the careful management of energy and the clever conservation of activity to ensure continuity for as long as possible. Furthermore, some speculative ideas suggest that extremely advanced life could manipulate the very structure of space and time, bending cosmic rules to extract new forms of energy or to stabilize regions of the universe. Dark energy, the force driving the universe's accelerated expansion, might be harnessed as a power source. Quantum fields could be tapped for energy that seems inconceivable by today's standards. These concepts, while far beyond current technological capabilities, illustrate the incredible ingenuity that life might develop in the face of a universe that is slowly becoming inhospitable. Even as civilizations adapt and technologies evolve, there may come a point where the fundamental conditions of the universe, its vast expansion, freezing temperatures, and dwindling energy, become too extreme for any form of life to endure. Yet the sheer range of possibilities highlights how creativity, adaptation, and survival are intertwined with the ultimate fate of the cosmos. Life might persist far longer than we can imagine, evolving in ways that are entirely unfamiliar, operating under principles we do not yet understand, and exploiting phenomena that today seem purely theoretical. The acceleration of the universe's expansion also gives rise to another fascinating scenario known as the Big Rip. In this vision, the stretching of space itself becomes so intense that it eventually overcomes all other forces. Galaxies would be torn apart, stars ripped from their orbits, planets flung into the void, and atoms themselves could be pulled apart. The universe, in this extreme future, would be fragmented into isolated particles, scattered across ever-increasing distances. Unlike the gradual quiet of the Big Freeze, the Big Rip is violent, an unravelling of the very structures that define matter. While it is more dramatic, it also depends critically on the exact properties of dark energy, a substance that remains mysterious and poorly understood, even with the most advanced observations of distant supernova, cosmic microwave background radiation, and the large-scale structure of the universe. The interplay between these different end-of-universe scenarios highlights the remarkable complexity of cosmology. The universe's fate is not determined solely by its current expansion rate, but by the intricate interactions of dark energy, matter, radiation, and gravity. Small changes in any of these components could dramatically alter the outcome. For example, a change in the density of matter could tip the balance toward a slow contraction rather than perpetual expansion. A shift in dark energy's behavior could transform a gentle drift into an unstoppable rip. Quantum fluctuations could suddenly create bubbles of true vacuum, rewriting the rules of reality. In all these ways, the future is both constrained by the laws of physics and open to phenomena that challenge intuition and imagination. Throughout this vast canvas of possibilities, the role of time itself becomes staggering. When scientists speak of billions, trillions, or even quadrillions of years, these are spans that defy human comprehension. The universe may endure for such vast periods that countless cycles of star formation and extinction, galaxy mergers, and planetary evolution will occur before any ultimate ending arrives. Life, if it survives, would experience epochs so long and slow that even civilizations with lifespans measured in centuries or millennia would seem fleeting in comparison. The scales of space and time in these scenarios dwarf the familiar rhythms of human existence, inviting reflection on both our place in the cosmos and the resilience of living beings against extraordinary odds. Even in a universe moving inexorably toward heat death, there remains room for adaptation, ingenuity, and survival. Civilizations could evolve strategies unimaginable to us, finding ways to manipulate energy, store heat, and extend the longevity of biological and technological systems. Life could migrate to regions of space that remain relatively warm for longer periods, take refuge near the last active stars, or orbit black holes as long-term energy sources. Artificial intelligence, machines, and engineered organisms could carry on the functions of life even as organic forms fade. In this sense, the story of the universe's end is also a story of creativity and persistence, of the ability of matter organized in the form of life to resist entropy and decay in extraordinary ways. The sheer diversity of theories also underscores the uncertainties that remain. Dark energy is poorly understood. Its origin, nature, and future behavior remain one of the greatest mysteries of modern physics. Quantum mechanics hints at processes that could alter reality instantaneously, while the possibility of the multiverse expands the canvas of speculation to realms beyond observational verification. These uncertainties mean that the ultimate fate of the universe is not a simple story with a single conclusion, but a complex web of interrelated possibilities, each governed by fundamental laws yet shaped by factors that may only become evident in the farthest reaches of time. In considering all these outcomes, one cannot help but reflect on the scale of cosmic change. Stars that now shine brilliantly will eventually burn out, leaving remnants such as white dwarfs, neutron stars, or black holes. Galaxies that cluster today will drift apart under the influence of accelerated expansion. The very elements forged in stellar furnaces will eventually disperse, recycled over countless eons until they become thin, cold clouds scattered across an ever-expanding space. The processes that currently sustain life and structure will slowly fade, replaced by a universe that is fundamentally quieter, darker, and colder than the one we know today. Yet even in the most extreme projections, the potential for persistence and adaptation remains astonishing. The universe's vastness allows for countless niches and opportunities where energy might be harnessed, structures maintained, and life extended in forms that defy our current understanding. The interplay between cosmic expansion, gravitational attraction, dark energy, and quantum phenomena provides a canvas of possibilities that is both intricate and awe-inspiring. Life, if it can continue, may exploit every subtlety of physics, discovering methods to endure that would seem miraculous from today's perspective. Throughout this exploration of the universe's end, one theme emerges repeatedly. Change is constant and outcomes are diverse. While stars fade, galaxies drift apart, and temperatures plunge, the cosmos offers mechanisms and phenomena that could, under the right circumstances, preserve matter, energy, and even life. From harnessing black holes to surviving in extreme environments, from slowing metabolism to manipulating quantum fields, intelligent beings might extend their existence far beyond the lifetimes of individual stars or galaxies. The universe's vastness, its forces, and its possibilities create a stage upon which survival, adaptation, and ingenuity might continue for epochs that stretch far beyond human imagination. Even as the universe expands toward a state of immense cold and darkness, the story of matter and life may continue, shaped by creativity, intelligence, and the laws of physics. Each scenario, from the slow heat death to the violent big rip, from the improbable big crunch to the mysterious quantum vacuum decay, reveals a different facet of the cosmic future. The interplay of expansion, gravity, energy, and quantum phenomena ensures that the fate of the cosmos is rich with possibilities, each more extraordinary than the last. The universe, in its immense complexity, continues to invite curiosity, speculation, and wonder, offering a panorama of potential endings that stretch from the quietly cold to the violently transformative, from the unimaginably slow to the instantaneously catastrophic, and from the familiar laws of physics to realms that challenge imagination itself. In this ever-expanding web of ideas, life, if it can endure, faces challenges that are almost beyond comprehension, yet the potential strategies for survival reflect an extraordinary ingenuity. Civilizations might endure by controlling energy, building artificial environments, harvesting black holes, or exploiting subtle aspects of the universe that we barely understand today. The persistence of life may hinge on its ability to adapt to conditions that are alien, extreme, and far removed from those on Earth. The concepts of energy, time, and matter would take on entirely new significance as civilizations stretch resources across eons. In such futures, the survival of life becomes not just a biological problem, but a cosmic engineering challenge, demanding understanding and manipulation of fundamental physical processes on scales that are both immense and subtle. Even as the universe becomes colder and emptier, the vastness of space might provide opportunities for survival in pockets where energy and matter remain accessible. Structures could be maintained near the last glowing remnants of stars, or life could cluster around energetic phenomena such as black holes or neutron stars. Technology might allow the preservation and recycling of energy in ways that seem almost magical to us today. The concepts of life, survival, and civilization might evolve into something radically different, functioning with efficiencies and processes unimaginable under current conditions. Evolution, ingenuity, and the laws of physics could combine to sustain existence far longer than one would naturally expect. In these extreme futures, civilizations may become extraordinarily patient and meticulous, carefully rationing energy and controlling activity to endure for unfathomably long periods. Time itself could become a resource to be managed with precision, stretching the smallest reserves of energy across vast expanses of eons. Life might not rely on speed or immediate consumption, but on slow, deliberate processes, extending survival far beyond conventional expectations. These adaptations might involve physics and technologies far removed from anything known today, reflecting a deep understanding of the cosmos and its potential resources. All of these scenarios, from cosmic collapse to gradual cooling, from quantum vacuum instability to infinite expansion, illustrate the delicate interplay of forces that determine the universe's destiny. Gravity, dark energy, matter, radiation, and the laws of quantum mechanics weave a complex tapestry, one in which the past, present, and future are intimately connected. The universe's story is one of unfolding change, in which the structure, energy, and potential for life evolve continuously. Even as galaxies drift apart and stars burn out, the possibilities for adaptation, survival, and innovation highlight the resilience inherent in matter and life itself. The exploration of the universe's end is a journey through time and imagination. It forces the mind to confront scales of billions, trillions, and even quadrillions of years, to consider the fates of galaxies, stars, planets, and civilizations across epochs far beyond human comprehension. It raises questions about the nature of existence, the persistence of life, and the potential for intelligence to endure and adapt when confronted with a cosmos that is ever-changing, ever-expanding, and filled with forces that both sustain and threaten it. These reflections, rich in complexity and imagination, continue to inspire scientists, philosophers, and dreamers alike, inviting humanity to ponder its place in a universe that is at once vast, beautiful, and profoundly mysterious. The universe's expansion, the accelerating retreat of galaxies, the mysterious force of dark energy, and the strange possibilities suggested by quantum mechanics all combine to create a panorama of potential cosmic endings. Each possibility, whether the violent disassembly of the Big Rip, the quiet fade of the heat death, the collapsing convergence of the Big Crunch, or the sudden unstoppable transformation of vacuum decay, presents a vision of a future that challenges the imagination. These futures, spanning incomprehensible stretches of time and unimaginable scales of space, reveal both the fragility and the resilience of structures and life within the cosmos. In considering the ways life might persist, it is essential to remember that survival may demand ingenuity, patience, and a profound understanding of physical law. Civilizations may evolve strategies that leverage the smallest sources of energy, exploit the last surviving stars, or even manipulate the very fabric of space-time to extract power and extend existence. The universe may become a realm of carefully managed energy, slow metabolism, and meticulous conservation, where survival depends on both technological prowess and the capacity to endure vast spans of time. Life, in this vision, becomes an exercise in cosmic persistence, a testament to adaptation under extreme and changing conditions. Even as the universe approaches the vast emptiness of its long-term future, the interplay of cosmic forces, gravity, dark energy, radiation, and quantum fluctuations ensures that the story of existence remains intricate, compelling, and unpredictable. Galaxies may drift apart, stars may fade, and matter may grow cold and diffuse, yet within these grand processes lie the possibilities for life to adapt, technology to flourish, and intelligence to persist. The ultimate fate of the universe, whether it involves slow cooling, sudden destruction, or speculative multiversal transformation, presents a canvas on which the resilience of life, the ingenuity of civilizations, and the subtle play of cosmic forces can all unfold. As the universe keeps stretching and expanding over time, the distances between galaxies slowly become enormous. Galaxies that were once relatively close will drift further and further apart. For any civilizations that might exist out there, this growing separation would gradually make contact harder and harder. At first, it might just take longer to send messages or travel between galaxies. But as the expansion accelerates, it could eventually happen so quickly that galaxies move away from each other faster than light itself. When that happens, no form of communication or travel between galaxies would ever be possible again. Each civilization would find itself trapped in its own tiny corner of the cosmos, like an isolated island in a vast and ever-growing cosmic ocean. This kind of isolation would be unavoidable because space itself is stretching without pause. No matter how advanced a civilization might be, the distances imposed by this expansion would be insurmountable. As the universe moves toward what scientists call heat death, the picture becomes even bleaker. In that distant future, trillions upon trillions of years from now, the universe would cool steadily. The temperature everywhere would sink closer and closer to absolute zero, the coldest temperature nature allows. At this point, even the most basic physical processes like chemical reactions or the motion of atoms would slow dramatically and eventually stop altogether. Life of any kind, even the most intelligent or energy efficient, needs energy to survive. In a universe that is almost completely frozen and starved of energy, even simple tasks, thinking, moving, reproducing, or maintaining a functioning body would become impossible. Eventually it could reach a point where the energy required just to survive cannot be found anywhere. Yet some scientists and visionaries imagine extraordinary possibilities. Could life, far in the future, change in a way that doesn't rely on energy as we know it? Could it evolve beyond carbon-based chemistry, or even lose the need for a physical body entirely? One striking idea is that life could become purely informational, existing as patterns of data or consciousness stored in digital or quantum systems. In this form, life might persist long after the universe becomes too cold for anything biological to survive. Such beings might no longer age or decay in the usual sense. If this transformation is possible, life could continue almost indefinitely, even as the universe itself fades. Some even more daring ideas suggest that life might escape this universe entirely. The theory of the multiverse proposes that our universe is only one of many. Other universes could have entirely different laws of physics, matter, or conditions more favourable to life. If a civilization became advanced enough to travel between universes, it might leave behind a dying cosmos and settle in a fresh universe filled with possibilities. But long before the universe reaches that cold and silent end, the first signs of this grand change would appear in the breaking of communication between galaxies. Right now, galaxies are still close enough, on a cosmic scale, to be observed through powerful telescopes. Yet as space continues to stretch faster and faster, galaxies will drift beyond reach. Eventually they will slip past what scientists call the observable horizon, vanishing from sight forever. Not only would they disappear visually, but no signal, radio waves, light, or even the most futuristic communications would ever reach them. Nothing can move faster than light, and as galaxies drift apart, the expansion of space itself would surpass even the fastest signal, This growing silence would have profound consequences. If intelligent life exists elsewhere, the early universe might have offered a brief window when intergalactic contact was possible. But as expansion continues, that opportunity would disappear completely, leaving each civilization alone in its part of the cosmos. In the distant future, each galaxy, or more accurately, each cluster of galaxies bound together by gravity, would become a self-contained cosmic island. No bridge could ever cross the vast emptiness separating them. The rest of the universe would grow dark, silent, and unreachable,